Yeah, I hope you all slept well and the food and digested the food well. It was amazing, I think. First of all, I would like to thank the organizers, Arnaldo and Axel, for the invitation. It's really a great pleasure to be here and present our work. So I'm going to change a little bit the subject. We heard a lot about cold atoms over the last days. I will talk about a new type of quantum gas that we recently realized in the lab, namely optical quantum gases. So quantum gas is made out of light. But since still it's a cold atom meeting and I have a background in cold atoms as well, I will also discuss recent work that we did using ultra-cold bosons in 2 dimensions in a box potential. In particular, what I will be discussing is the first measurements of the compressibility and the equation of state in such optical quantum gases. So the people that I should acknowledge first are on the University of Bonn side, Eric Busley, Leon Espert, and Fari Öztürk. This was done in close collaboration with Martin Weitz. So these people are all working on photonic systems. And on the other side, during my postdoc, I was collaborating with Zoran Hasibabic. And here the main protagonists were Panos Christodoulou and Maciej Galka. And I will discuss experimental work that we did in both of these projects under the overarching theme of 2-dimensional Bose gases in a box. So suppose that I would give you an unknown substance. You don't really know what it is. Let's say it would be a gas or a liquid. And I would ask you to characterize this system. Of course, you could perform some elaborate technology or a spectroscopy method. For example, you could look at the conductivity of such a system. You would be able to characterize the system in a very detailed way, but a very intuitive way of characterizing a system is just by looking at its mechanical response. So actually, what you would do is you would just compress the system, and so you reduce the volume, and then you look how does the energy change in the system. So it's a very simple concept, and it turns out that it's a very valuable tool to identify states of matter, also quantum states of matter, and phase transitions between them. The compressibility is well known for many-body systems, for different realizations of many-body systems. Randy, for example, talked about the Mott insulating state. Here we have basically an incompressible system. We have one particle sitting at a lattice side. So this would be more from the solid state field, actually, although it has been realized with cold atoms. So intrinsically, we have one atom per side, and there are no fluctuations in the system. Then going towards superfluid systems of liquid helium, we have strong interparticle interactions, and that makes it actually energetically very costly to reduce the volume of such a system because of strong interactions. And for ultra-cold atoms, where we can realize BECs, of course, we have the tool of Feshbach resonances, so we can tune interactions, and here the compressibility can become significantly larger. It does not have to be a very incompressible system. So here, these systems actually can be tuned. This has been understood fairly well for material particles or systems of material particles. What is not really known is what about light matter systems? So systems that somehow consist of photons that couple to a material component. And this is what we call optical quantum gases. And these systems are typically realized in optical cavities. So somehow you need to build a container for photons. And of course, these are typically mirrors. And the constituent particles often are simply photons, or they are actually dressed photons, so-called exciton polaritons. I believe we hear more in the next talk by Marzena. So the compressibility is a very central property that tells us a lot about the physics of the system. For example, it can give access to the equation of state. It's actually a direct manifestation of the equation of state. It tells us about fluctuations as seen for the Mott insulator. It characterizes transport properties and elementary excitations such as sound. And we will see that's important for all the systems that I will discuss in the remainder of this talk. In order to have some well-defined systematic setting, you want to confine these samples into something where you have a well-defined volume. Okay, so the idea is to take these photons and put them in a box. But we have to do that in a low-dimensional space. We have to do that actually in 2 dimensions in order to study them. So these homogeneous Bose gases or Bose quantum gases in 2 dimensions have in recent years really made quite some progress, and I want to share some of the insights that we gained. Here I'm showing a somewhat like sketchy phase diagram. So you have interactions, and on the x-axis you have equilibrium towards out of equilibrium. In the equilibrium region at strong interactions, you can confine atoms in these optical box potentials made out of sculpted laser beams. Here, this is just a Laguerre-Gauss, and you have two light sheets. And if you just move these light sheets close to each other, you can actually realize these uniform traps. In this case, it's a rectangular shaped one. And of course, there has been a lot of work in the group by Jean Dalibard and also other groups around the world. Then you can move this system. Basically, the idea here is to study BKT physics. Then you can move this system towards the out of equilibrium regime, and you can ask yourself, can I learn something about turbulence? How does turbulence emerge? Of course, I have a very clean setting, so can I look actually at the emergence of a cascade in the system as I drive it out of equilibrium? Then reducing interactions, there have been works in the field of exciton polaritons. Also there, it's possible to implement box potentials. And these are, you can see here in this region, the system is pumped so that realizes a repulsive potential well, and the polaritons are trapped in the center. And because these are very strongly non-equilibrium systems, you can investigate new physics, such as the topology in the vicinity of exceptional points. Exceptional points are really like a hallmark of non-equilibrium physics. The work that I will be focusing on in terms of the weak interaction, again, goes a bit closer towards the equilibrium regime. So here, the goal was to realize photons inside such a box potential to get such a nice uniform density distribution and investigate the bulk properties of this sample. So we see here that we somewhat invert the paradigm. While we here realize traps made out of light for matter, we here trap light inside potentials made out of mirrors or matter. So it's exactly the reversed scheme. Okay, so this brings me to the outline of my presentation. In the first part, I want to talk about ultra-cold atoms in a two-dimensional box potential. In particular, our study on first and second sound in a BKT superfluidity. In the following, I will discuss the emergence or studies of the emergence of turbulence in such a two-dimensional trap. And in the second part of my talk, I will then move to optical quantum gases in 2 dimensions, show you the measurement of the compressibility and equation of state, and more recent work where we use this low-dimensional system to identify a fluctuation dissipation relation, actually for the first time in a Bose-Einstein condensate, based on the number fluctuations. Okay, so BKT superfluidity, named after Berezynski, Kosterlitz, and Thouless, the very unconventional state of matter, if you want. It emerges in 2 dimensions, and as we all know, in 2 dimensions in an infinitely large system, you would actually not expect Bose-Einstein condensation to occur because you have fluctuations. In other words, the first order correlation function actually goes to 0 as 2 points are spread by a very long distance. So that means there's no long-range phase ordering. However, already like 50 years ago, Kosterlitz and Thouless identified theoretically that there is a mechanism that restores superfluidity in these systems, and this superfluidity is induced by topological defects. And of course, this one is not a quantized one, but it gives you the idea of it. These topological defects are, of course, vortices. To give you some illustration of this BKT mechanism, how does it occur, and what's the nature of it, at least intuitively. This is a phase transition of infinite order between 2 phases, and these phases are disordered. Here I'm showing 2 examples of 2 different gases prepared at different temperatures. So at the high temperature, you see this sample here. It's full of free vortices, and these free vortices scramble up the phase of the system, leading to an exponentially decaying correlation function. So this gas is quantum degenerate, but it's not yet superfluid. So there's no algebraic order. As you cool down the system, you then observe a superfluid with weak disorder. So here there are still some phase fluctuations, but they are related to phonons. And these vortices now form bound pairs. They can also be higher order, higher order dimers. But in first order, you consider bound pairs. And that, of course, restores the phase coherence in your system. And you have a correlation function that decays algebraically. Of course, this algebraic decay is associated to the emergence of a superfluid. Now, how can you identify the difference between these two different phases? Of course, you could look at the correlations, but since it's an infinite order phase transition, any thermodynamic quantity will actually smoothly cross. There's no divergence in the specific heat or in any other thermodynamic quantity. However, there has been a prediction for one discontinuity, and that is related to the superfluid density in terms of the universal jump. So what happens is you cool down the system, and then rapidly this superfluid phase space density, Ns times lambda squared, actually jumps to a universal value of 4. And this value is universal, meaning that it's independent of interaction strength. Again, quite some time ago, 20 years ago, there have been quantum Monte Carlo calculations by Prokofiev and Swistunov, and they were actually seeing this jump. Here's the superfluid fraction as a function of the temperature. You cool down the system, it jumps up. But this has experimentally never been seen. And of course, as an experimentalist, you are interested in observing this feature. The question is just how. And in 2014, Sandro Stringari and co-workers actually proposed you should do the following, inspired by old work from the helium community. In fact, you should look at sound propagation. So in such a two-component system, you have a normal fluid and a superfluid. These two components actually then give rise, in terms of hydrodynamic equations, to two sound modes. You can have either both oscillating in phase, so that would correspond to a density wave. That's the first sound. But you could also have an out-of-phase oscillation. You see basically the density is constant, but what you change, of course, is the entropy. Here you have a very low entropy, here you have a very high entropy. Yeah? So here it's mostly superfluid, and there it's mostly normal fluid. And that is known as the second sound. Of course, what I'm showing here is all in terms of the language of liquid helium. But what is important to note is that the sound speeds that you can deduce from these experiments contain a lot of thermodynamic quantities, but in particular, they contain the superfluid density. You see this term Ns appearing in the second sound velocity. So measuring the sound velocity actually can become a tool to access the superfluid density. And for very low compressibility, of course, this was done many years ago by Peshkov in the helium-2 samples. So what we set out to do with cold atoms was to realize a two-dimensional uniform box trap. This is just realized with the conventional methods that are available nowadays, or that we can straightforwardly develop in the labs using digital micromirror devices. So in one direction, you confine atoms in this kind of lattice, which we are able to compress. And the in-plane confinement is done with a second beam. So this is a hollow rectangular shaped beam. It looks red, but it's still blue detuned. So that's a bit confusing, but it's a repulsive potential for the atoms. And you see this rectangular shaped cloud trapped in the system. You need to take care of, in order to realize these hydrodynamic conditions, that you actually have many collisions between your particles. So here, the reason, basically the reason why we studied this and why we were quite optimistic to observe these effects was because we had a potassium-39 gas, and there you have Feshbach resonance with tunable interactions. So we went to relatively large G tilde of 0.64. Crucially, that also leads to a fairly compressible system, and I will explain the implications in a minute. What you then do is you start shaking. You don't shake as hard as Wanderley was shaking his clouds. Actually, you have to be very gentle to just only excite the lowest lying mode of your system. So you apply an in-plane magnetic force. Actually, it's a field gradient that pushes the atom to one side, back to the center, to the left side, and so on. And so this is important to note, that we just excite this lowest lying mode, and then we observe two different sound modes hopefully, in the system. Here you can see the response of the center of mass. So we are shaking along this direction, and we look at the center of mass, and you see nicely how this follows our drive frequency. So this is a periodic driving at omega, and from the response, we can fit this in a very general way. We can extract actually the out of phase. So this is sine, this is a cosine. So this is the out of phase response that gives you the absorptive part, and thus directly the density response function. But first, before going more into the experimental details, I want to quickly discuss what is actually expected in this limit for the 2D Bose gas. And of course, the theory that you start with is the Landau two-fluid model. So this is essentially the total density of your system is the sum of the superfluid and normal component, and the same holds for the total current. And then what you investigate is actually a perturbation at low frequency, smaller than chemical potential and collision rate. And this perturbation obeys two wave equations. Again, this is connected to first and second sound, obviously. One governs the density and one governs the entropy. And this together gives actually a quartic equation for the speed of sound. So you see it's c to the 4, c squared, and here it's basically no dependency on the sound velocity. And if you solve this, so the coefficients here, they just depend on the thermodynamic quantities, and also they depend on the superfluid density. So this gives rise, by normalizing over the Bogoliubov speed of sound, to two sound branches, which are just functions of t over tc, actually, which is relict. We heard this yesterday in the presentation on the Bose gases from the Paris group, that scale invariance actually makes this only a function of t over tc. Here's the expectation theoretically for G of 0.6 comparable to the experimental conditions. And you can see in the normal phase at high temperatures, we just expect one sound. That's just a normal density perturbation propagating to your sample. However, if you cool down the system, you see these two branches. You see the second sound and the first sound. First sound, by the way, because it arrives first, it's faster. That's the definition of the first sound. And what you in particular see is that there is a discontinuity visible in both of these sound branches, and they reflect the jump of the superfluid density. So what we see here is this jump, and also a little jump here, and this comes from the fact that our systems actually has a finite compressibility there. So there's a bit of a mixing between the two sound branches. So in fact, yeah, it's actually due to this term, but I don't have time for details. So we set out to do these experiments. We were starting to shake the cloud. As I said, we do this at a wavelength of pi over L. And here I'm showing two different response spectra. So basically what you do is you shake this cloud at different frequencies, and then you record the response, imaginary part of psi, and via the fluctuation dissipation relation, you directly obtain the dynamic structure factor, which is shown on this plot. So there are two spectra shown here, one at high temperature, which is the red curve, and one at low temperature, which is the blue curve. The high temperature one just shows one single sound resonance, and in addition, we see this peak at omega 0. That is not a sound mode, but it's actually a diffusive heat mode that just comes from the fact that you have another differential equation that describes actually the propagation of heat through your system. But as we cool down the system below the critical temperature for BKT, we see nicely resolved these two resonances corresponding to the first and the second sound. So this is just two examples for two different relative reduced temperatures. And of course, we can do this at many more temperatures. And we have done so. And you can see here in the same style as before, as a function of the temperature, the normalized speed of sounds with the two branches. And above the critical temperature, we see nicely only the first sound mode propagating, and then the emergence of two sound branches. And then using the thermodynamics, we can use this information, of course, to extract the superfluid density and also the superfluid phase-space density, which is shown here. Superfluid phase-space density as a function of the total phase-space density, with a jump occurring at the critical value that is precisely on the order of 4, or roughly larger than 4. Okay, so this was essentially the first part. It was really like kind of one of the outstanding goals in the field of 2D Bose gases, and here by pushing really to this high interacting regime, we were really able to observe this. So that was quite satisfying to see this theory actually match with the experiment in the end. Okay, that brings me to the second part of the presentation. I want to drive the system now stronger and see if we not only stay in the lowest mode of the gas, but actually go to higher states, what happens? And of course, we already had a very nice introduction by Vanderlei yesterday on turbulence, so I don't want to spend too much time on it. I just want to give you an idea about the general concepts that we would expect, or the key signatures that we would expect. Of course, turbulence has been fascinating scientists and human beings in general for centuries, from Leonardo da Vinci to more recent works, for example, by Richardson, who wrote this nice poem-style piece on saying, which actually describes what happens in turbulence. Big worlds have little worlds which feed on their velocity, and little worlds have lesser worlds, and so on to viscosity. So this means you inject at some large scale energy, and then this energy flows through your system over different length scales. The length scales become smaller and smaller, and eventually the system dissipates the energy at a very small length scale, corresponding to a very large wave vector. That's a cascade, and this cascade has the key signature of k to the minus gamma as a momentum distribution. And in our case, we look at worlds which are waves, so we don't consider vortex turbulence, and the viscosity is actually trapped at the trap depth. So the viscosity is set by the maximum energy that is allowed in our system. So how can you picture this in a very simple way? It's just an illustration of the birth of 2D wave turbulence. So you can think of some tabletop fountain, and you inject in the center some perturbation. And of course, you know that the water at some point will drop down this table. This is where dissipation happens. But of course, the question is what happens in between? And is it possible to look at this in more detail, to actually perform microscopy in some sense, to learn about how does turbulence emerge? And of course, in 2D, I have to emphasize this. This low dimensional system, of course, is famous for inverse cascades. So actually vortex propagation from high K states to low K states. So it's the opposite direction, which we are, however, not studying in our work. So we are only focusing on wave turbulence. So in a very similar picture, this is actually what is happening in our experimental scheme. So it looks a lot like the fountain before. This is momentum space. And what we do is we inject energy in an anisotropic fashion. So we shake along one dimension, and that of course promotes particles into some excited Kx state. And eventually there will be some microscopic interactions forming some statistically isotropic cascade front that then propagates through your system until it is dissipated at the dissipation scale Kd. So this direct cascade is connected to certain key concepts. As I said already, you have an anisotropic injection and isotropic propagation. So there's something going on with kind of like the system forgets in which way it was driven. And also before it reaches the steady state, there have been theory predictions, and we heard a lot about this, that there's actually a dynamic scaling occurring of your momentum distribution, which is also known as basically this self-similar propagation of your momentum distribution, which can be written down via this equation. And by simulating, we can actually see what is happening. This is done for a three-dimensional Bose gas, and taken from this paper, you can see that this cascade front is actually propagating as a function of time. And all this is happening in a self-similar way. So if you would rescale the x-axis or the k-axis, they would collapse. Just based on some energy arguments, we can already make some statements about what are the exponents in the system. And because this is forced turbulence, so the energy will actually grow with time. And based on these arguments, we can make some estimations for beta, or predictions for beta, that it should follow 1 over the dimensionality plus 2 minus the power law of this steady state, or basically of the cascade front that of the cascade, sorry, that propagates. Okay, how do we implement this in the experiment now? This perturbation, of course, is connected again to pi over L. This is our fundamental mode that we are driving. Then in the intermediate region, we have the 1 over the healing length, and eventually the dissipation scale is given by KD. And we do all this in momentum space. And of course, what is happening, this is a double log plot, by the way. So this is energy as a function of momentum. And you can see the energy is injected at this low K state, and then we expect it to propagate through this system and eventually get dissipated at some large KD scale. Of course, what we need to take care of, all this should be in 2 dimensions. So we want to go, in fact, weakly interacting, because the trap depth should always be significantly larger than this dissipation scale, and it should be much larger than K psi. So there are, again, some constraints that we need to take care of. How do we inject the energy then? And how does the steady state look like? We perform this anisotropic energy injection. So we have our square-shaped box potential in this case with a chemical potential of mu. And then we drive this with a force F. F times system length is just an energy. So this is a dimensional parameter that describes our driving strength. We excite energy, and this gives rise to the excitation of the first mode. And of course, this will propagate through the system until eventually it's dissipated and some steady state has built up. What we see is that if the driving is strong enough, for p larger than 0.5, we see an isotropic momentum distribution. And this follows a power law spectrum, k to the minus gamma. You can see this here as a function of k. And we've tested this for various system sizes, for various chemical potentials. And we find a quite robust value of this gamma equal to 2.9. So this value is, in fact, not equal to the dimensionality. Just from theory arguments, based for weak wave turbulence, you would expect actually gamma to be equal to 2, but that is not the case for our experiments, and we don't really know why, but one possible explanation could be finite size corrections, because our inertial range, of course, is very limited, spanning a little less than a decade. Okay, so we have seen there's anisotropic driving and there's an isotropic steady state, but let's look at this in more detail. When does anisotropy become isotropy? And we can do this, of course, in a box in 2D in a very nice way, because we can directly look at the in situ density modulations. And using principal component analysis, we can reveal the phonons that participate in this process. So here's the density written just as the mean density with some additional density modulation given by the principal components. These are just orthogonal wave functions, essentially, that describe the phonon modes and some time evolution and some weights. So if you perform this PCA, you can read more in this paper here by Hélène Perrin. You obtain certain eigenvalues which correspond to the weights, and we find that the most dominant eigenvalues correspond to functions that look as follows. Of course, we drive on this mode here, but then we see how the excitations actually go from the kf equal 1 to the to 2kf, 3kf, 4kf, and so on. So that's a very nice way of directly looking at how excitations propagate through your system, but it's anisotropic, right? So it goes just in one direction. And we are here, of course, with 4kf being 0.15 k psi, deeply in the phonon regime. So actually a cross-directional coupling is not really expected for this phonon regime. But this is kind of course, here we are limited by resolution, but we can use another technique, and that is Bragg spectroscopy. So we can just diffract the atoms on some standing optical wave and then eject basically atoms with a certain momentum class, and then again perform a spectroscopy of this system. And in this way, we actually can recover the fact that eventually our distribution becomes isotropic. Here's just a picture indicating this in momentum space. So we excite in an anisotropic way, and eventually it becomes isotropic at a large K. And these are just the projections measured by the Bragg spectroscopy. And this is shown here on the right-hand side as a function of K. So you can see eventually this was just going to 0.15 k psi which is roughly 1. So it was going until here. And now we have really ways to access even higher K states. And the important thing to note, here's a difference. So we see in one direction, there's basically all the atoms at low momentum in a low momentum class. However, in the other direction, there are more in the excited state or in the excited K states. And eventually here at K somewhat larger than 1, these two curves coincide. So that's the point where isotropy is supposedly emerging. Okay, finally, by performing time-of-flight experiments, we can also look at the cascade dynamics to get some access to this prediction for dynamic scaling. Here I'm showing compensated momentum spectra at different shaking times. So we shake the system longer and longer, and we see how this cascade actually propagates further and further to the right. And here it does not continue to propagate because it has actually hit the dissipation scale. So here we have a steady state that built up. We can look at the energy that is contained in this cascade. We see nicely it's growing in a linear fashion. So there's a constant energy injection into the system. And we also see that the cascade front propagates in this power law, in this algebraic way. And from this, we can, in fact, from our gamma 2.9, we can extract the beta value, which is just shown here as a solid line. So this is not a fit. This is just showing this result. Finally, these momentum spectra, we can also try to interpret in terms of this dynamic scaling. So we can rescale the different axes, and we can here in this way nicely see how all the curves during the propagation, so basically the left 4 collapse onto 1. And here the dynamic scaling breaks down for the red and the orange due to the fact that, of course, here the system has reached a steady state and the dynamic scaling is not expected to work anymore. By rescaling, of course, we have to choose our beta, and beta is, in this case, 0.85. We have measured the gamma of 2.9, and from this, together with the equation that I was showing earlier, we can deduce the effective dimensionality of this problem. Although it's off from the absolute ab initio predictions, we find that this corresponds to a 2-dimensional system within the error bar. For the future, some open questions on that direction, of course, will be also what is the relaxation dynamics after driving the system? How does coherence come back into the system? And also, what do these numbers actually mean? Is there some universality between different systems? And what are the exponents that are governing the dynamics, for example, in this case of relaxation dynamics? So can we actually learn something more from these exponents in terms of out of equilibrium universality classes? Okay, and so with this, I'm done with the cold atom part. I will now switch gears a little bit and go from 100 nanokelvin to 300 Kelvin. So it's 9 orders of magnitude change, but also photons are much lighter, obviously, than cold atoms. So that makes the difference. So I want to start with the compressibility and equation of state in a box-trapped 2D optical quantum gas. So I already was showing this before. How do you trap an optical quantum gas? Well, you have to use pretty good mirrors with a very high reflectivity. This is, of course, just an artist's view, but you can consider the photons traveling back and forth in this cavity, a multimode cavity, as some effective gas. And of course, photons don't interact with each other, but you need to couple them to some bath in order to thermalize. So there are also some material particles, in our case, molecules in there, and the photons are interacting with these molecules in order to attain thermal equilibrium. The concept, more in a sketched way, to realize such a photon gas is by using a dye-filled microcavity. This microcavity consists of 2 highly reflecting mirrors, and in this case here, these are curved mirrors, and they are spaced only by roughly the wavelength. We insert dye molecules in a solution at room temperature, and what happens is that after exciting the system with an external pump beam, the molecules are excited, they emit fluorescence photons, and these photons, they actually don't leave the cavity. So it's not like in a laser that you want the photons to go out, but you want to trap them for a long time. And that's realized by a very high reflectivity, such that a photon eventually hits the next molecule, emits another fluorescence photon, and so on. So there's also some kind of cascade between absorption and emission events going on, which shift the frequency of each photon, omega, omega prime, and so on. So there's energy exchange between the molecules and the photons, and that leads to a thermal equilibrium of the photon gas due to the fact that the emission and the absorption of these dye molecules somehow contain thermal energy information. So there's a scaling with a Boltzmann factor. This is also, I said this already, it's also a deeply two-dimensional system. And how can we see that? Here on top, I'm showing the dispectral distribution of these molecules, the emission one and the absorption one as a function of frequency. So absorption always occurs at higher energy. So you have the Stokes shift here. And now this cavity has such a short cavity length that the free spectral range becomes very large. And different longitudinal modes correspond to different Qs here. And the spacing is so large that it exceeds the bandwidth of the dye. So photon emission and absorption will only occur into one of these manifolds, in our case, Q equals 7, and all the lines on top actually indicate transverse excitations. So photon not propagating only on the optical axis, but also with an angle with respect to the optical axis. And this constraint actually makes the system deeply two-dimensional. So you can think of this as a trapping frequency. The free spectral range is something like h bar omega z, and it's much more 2D than any cold gas, at least that I know of. What is also important is the chemical potential in the system is non-zero. So this photon gas is not like a black body radiator where mu becomes 0, but we are able, thanks to this to these molecules and the energy offset in there, to engineer a finite chemical potential. In this system, already 10 years ago or so, we observed Bose-Einstein condensation in a harmonic trap. So that's very close to the early work by Vanderlei and Dan Kleppner, I think. So really observing Bose condensation in a harmonic 2D trap, and this occurred at a measured photon number of 80,000 photons. So here I want to point out, this is a room temperature system. So how is it possible that we have similar numbers as with cold atoms for this critical particle number? Well, it's due to a very high trapping frequency. We have 40 gigahertz of trap frequency in the system as compared to a kilohertz or so with cold atoms. Several signatures could be obtained, for example, spectral and spatial distributions. Here you see the energy at different total particle numbers, so this is vertically shifted. Here you see just a Boltzmann-like occupation of these high energy states, and then eventually a macroscopic occupation of the ground state, and the same is visible in the spatial distribution. Here you see the Gaussian Maxwell-Gaussian distribution, and here a bright spot that corresponds to the condensate. And also, of course, we've investigated the emergence of coherence in the system. In this cloud, you just have a thermal de Broglie wavelength that determines the coherence length of 1.5 micron. Again, similar number as in cold atoms due to the very light mass of our photons. But I will say more to that in a second. And in the condensate, we have the emergence of spatial coherence in a transverse direction. So why are these photons massive? Well, because they live in 2D. So the idea is that you want to use this microcavity in order to modify the photon dispersion. So usually you would have a photon which is just linear with a wave vector, right? It's h bar times k times c. However, if you choose a very large longitudinal wave vector, which comes from the fact that we have a small cavity spacing, that allows you to expand in the paraxial approximation this expression, and this kz is actually frozen out. It's translated in some rest energy term, and it can be identified as an effective mass, and it's essentially 10 to the minus 36 kilogram. So it's a very small number as compared to cold atoms. But what is also visible, and then this leads to this kind of parabolic behavior of the energy with respect to the wave vector. And what is also visible is that the local spacing of your cavity also shifts the energy at positions x and y. So this can lead to a 2D massive Bose gas in a trap. And as I discussed before, this has been done in the past using harmonic traps. Here you have a delta D, so a cavity spacing that scales with R squared. You see these are these spherically curved mirrors, or we were able to also realize smaller traps which are close by, which actually lead to a coherent coupling. So we observed here coherent Rabi oscillations between these states. Of course, this is all due to the fact that you have an R squared scaling. In our new work, however, we used a novel technique to modify the surface of these cavity mirrors with nanostructuring techniques, so they are locally elevated, and then trap the light in between. So this is just 30 nanometers of elevation, and the light is then trapped inside this box potential. And as you can see, the density looks completely different as here. It's a really nice flat top distribution that allows us to look at the bulk properties of this gas. So here's the scheme to analyze a uniform photon gas in a very simplified way, of course. But this is the cavity. We have the dye molecules, the photons. And the photons will occupy the states available in this trap. And some light, a few, actually, it's a very small amount of light that comes out of this cavity because it has a very high reflectivity. It's then collected with a microscope, and we can image this. And we can image this in real space and in momentum space. On top, you see the surface density. This is just a normal phase gas. So it's a classical gas in this situation, no quantum features. So you see the density is somewhere far below 1. And in momentum space, you see kind of the corresponding interpretation. This is a Gaussian distribution that is cut off at some wave vector that corresponds to the trap depth. Of course, we cannot trap light. These walls are just of finite height, so we cannot trap light beyond this value. And of course, you can extract what is the variance, what is the width of this distribution, and this should correspond and reflect the temperature of your gas, and it's in very good agreement with room temperature. So we have a 2D homogeneous room temperature gas made out of light. What you want to try now is, what about Bose condensation in 2D? Everyone always says, well, it's not possible to see Bose condensation in 2D, but of course, the situation changes if you have a finite size system. For this, we prepared photon gases with increasing total particle number. You can see below 3,600 or so, this is a flat top density distribution. And then eventually there's a density increase observed here in the center, which then completely becomes dominated by the lowest lying state in this box potential. So this is nothing else than the sine squared eigenfunction of your trap. And the reciprocal space shows the exact same behavior. We can here observe again the Maxwell-Boltzmann distribution. And then gradually, as we increase the total photon number, you see more and more particles being concentrated in the vicinity of the lowest lying states. So here the center is basically Kx, Ky, 0, 0. And eventually, if the system is condensed, you see this bright spot in the center. And this is all very, let's say, high quality data in the sense that you can even extract the Heisenberg limited ground state here in this situation. But where does it exactly happen, this condensation? Well, we can do this for many photon numbers and count how many particles are sitting in the excited states and in the ground state. And we see very nice this BEC-like saturation. So the total photon number in the ground state is 0 and then increases at roughly 3,700 or so in this case, so it's 10 to the 4, and the excited modes actually start to saturate. However, this is a very soft transition, so that's indicating that there's no real phase transition, but it's a finite size effect. But what about finite size effects? Of course, we can make the system larger and larger. Basically, the idea behind the physics here is that the coherence length spans your entire system such that it undergoes condensation. So what if I make the system larger and larger? And we here go from, this is actually 40 by 40 micrometers. So we were able to realize even larger systems and then measure the critical photon number. And we see how it goes up in a slightly modified quadratic fashion. And this logarithmic term here is expressing the finite size effect of this condensation. So in fact, if I bring this L squared over here and the lambda squared over there, this is just a phase-space density, essentially. And it guarantees that if L is infinity, in a logarithmic fashion, also NC becomes infinity. So everything is fine. In a big 2D system of infinite dimensions, there is no Bose condensation expected. Okay, so now let's go to the compressibility of a photon gas. How can I measure the mechanical response of a photon gas? It's at first it's a bit maybe not so clear, but when you think about cavities and engineering potentials, it's pretty straightforward. What you have to do is you simply take your box inside this photon cavity and you tilt one mirror. And tilting one mirror implements a linear potential gradient that you superimpose. And of course, over the system size, this U naught over L is just a force. And by measuring then the photon displacement, very similar to the experiments I was showing before with the cold atoms where we were shaking. Here it's just a static displacement. You see nicely how the photons are pushed to one side according to this force. And from the center of mass displacement, X average over L, you can then, knowing precisely what U naught is, you can extract the compressibility of the system. So you want to do this. This is actually using local density approximation as well. So you can do this for various total particle numbers, or if you want phase-space densities, and in this way reconstruct the compressibility of the ideal 2D quantum Bose gas. And this is shown on the right-hand side. There's kappa T as a function of the density. So there are two regions, the classical region and the quantum region. In the classical region, what happens is just compressibility goes down. It becomes harder and harder to compress the gas as you have more particles in there, because it costs you simply more energy to compress them. However, the ideal gas theory is just this dotted line, which just continue to go down. That is not the case. Eventually, there's a change in the occupation going from Boltzmann-like distribution to Bose-Einstein quantum degenerate behavior. And you see this departure from this ideal gas prediction. You can see how quantum enhancement of the compressibility here emerges. And we can measure this up to the point which is roughly beyond the green data point where the system condenses. So all this is in the non-condensed phase. This here is where the system undergoes Bose condensation. We ignore this region because their local density approximation is not applicable anymore. Okay, so this is really a quantum enhanced effect, and it's a very sensitive system. As you can imagine, the photons, the chemical potential is essentially zero, close to zero. So small tilts of your box will lead to a displacement of your cloud, actually on the scale of the Bohr radius over the box size. Okay, and very related, this also gives us access to the equation of state. This has been, of course, measured for various settings with material particles such as ultra-cold atoms in 2D, 3D, mod insulators, with interactions without bosons, fermions, everything. It has never done for an optical quantum gas. And here's the result. So this is just the density as a function of the chemical potential, which we know very well because we apply this gradient potential, which is extremely well calibrated. And you can see nicely how this follows this. So basically, the red line is the prediction, and the data point nicely follows. The dashed line is for an infinitely deep potential. So that I have to say, that's basically, there's a modification in our data because we only trap, we have a finite trap depth, which is roughly 1.5 kBT. Okay, that brings me briefly to the last part of my talk, which is recent work where we studied the fluctuation dissipation relation. So I'm going away now from the Bose or the uniform gases in a box potential, but actually talk about harmonically trapped gases where we just have one BEC. And again, coming to this picture, of course, we have photons trapped here between our mirrors, but we should not forget that these are always coupled to molecular excitations. So what is happening in an experiment is that you would pump ground state molecules, M minus ME, they become excited and then they decay to become photons. The photons are reabsorbed and so on. So there's an exchange. And the total number of excitations here is a constant. That actually, if you choose the numbers right, can allow for particle exchange of your photon condensate with a reservoir. And that realizes or allows you to investigate a very interesting regime, namely Bose condensation in the grand canonical ensemble. So when it's coupled to a reservoir. So typically, if you have a small reservoir, you have a quiet Bose condensate, very weak fluctuations as a function of time. However, if I increase the reservoir, I see that there are strong number fluctuations occurring. I still have a strong occupation on average, but very large variance of my system. And that leads to this flickering Bose condensate. And we observed this already a few years back. However, what was still remaining open was actually what is the nature of these fluctuations. Is it due to the openness of the system, or is it thermal energy? And if you have a fluctuating system, of course, you want to ask yourself, is it possible to get some fluctuation dissipation relation? And very briefly, what we have as a tool in this system is that we can control the particle exchange with this reservoir by changing the energy cost for a photon and a molecule. This is in general a negative number. So a photon is always energetically cheaper than an excitation. And if I change the cavity length, of course, I can control these two numbers. And for a red detuned cavity, I have many photons and a few excitations, whereas for a short cavity, the photon costs me more energy. So I will actually have more molecules. And just from arguments on the free energy, you can ask yourself, well, how much can I reduce the free energy by creating a photon that will reduce by an h bar delta? And on the other hand, this is in competition with entropy inside the molecules. So this is just all the configurations that you have in excitations of the molecule and ground state. This consideration then leads to a photon number distribution. So in short terms, what is the likelihood to find n photons in the system? And we can see that for here shown for increasing condensate fraction, you can see this transition from a very broad distribution. So even at 25% or 50% condensate fraction, you can have a very broad distribution that is not Bosonian. And only approaches for very large condensate fractions is usually Bosonian-like limit. So here you have strong fluctuations coming from a large variance. From this probability distribution, you can, of course, obtain fluctuations and some response function. And this is what we recently tested. So briefly, we changed the cavity length because I'm running out of time, I think. We changed the cavity length that controls the detuning. And you can see that in this way, we are able to control this response function, dn over d delta. So basically, how many photons do I have upon changing the detuning? And on the opposite side, we can measure the fluctuations, which is this dashed line. And it turns out that this gives rise to this fluctuation dissipation relation shown on top. The experiments are done by looking at the clicks from photons. So just do quantum optics experiments. In some sense, this is not Hanbury-Brown twist, but it's the same technique. And we find the following result. Independently measuring this response function and the correlations, we find very good agreement between both sides. Here, I'm scaling the blue data by room temperature, T set to 300. But of course, we can also divide this data with respect to this data and then extract the temperature of 271 to perform thermometry based on fluctuations. Okay, so with this, I'm at my summary, and I have shown you measurements of first and second sound in BKT superfluidity and turbulence with cold atoms. And in the second part, I discussed novel studies with optical quantum gases and the fluctuation dissipation relation. These are pictures as a reminder. And for the future, we are particularly interested in looking for transport properties in these optical quantum gases. So my future will be mostly working with photonic systems, I have to say. And look for dissipation and non-local induced interactions and investigate, of course, what is the phase ordering in these uniform systems, and to realize lattice systems to look for perturbations that is actually possible. We have now new tools in these large systems, in order to investigate topological properties, I've recently been awarded the starting grant. So I've just started setting up the labs, and I'm really looking forward for this new direction. And in the long run, of course, the vision and the dream is to have this 100 by 100 lattice in this case to really study XY model, KPZ physics, turbulence, the role of impurities, the role of disorder on all these effects in this platform. And with this, thank you for your attention. And if someone's interested, there are positions available, and this is Bonn.
Thank you very much, Julian, for a very nice talk. Time for questions.
Thank you for the lecture. It was quite nice. I have a question. When you show that pictures, when we see a small dot of light in the square box, light concentrated in the center of the box, this can this be correlated with some kind of light localization, like Anderson localization, this kind of things?
Can you say again the first part of your question? I think I did not get. What was localized? Oh,
when can you go to the previous slide? That one that we can see the box. This one, for example, and we can see that there is a kind of concentrated dot in the center, right?
Yeah, that's the Bose condensate.
Yeah, but could we relate this with light localization, some kind of light localization?
No, this is not an influence that is induced by disorder or something. This is just, think of your box, non-interacting ideal gas. You have the different energy levels, and now you occupy these energy levels according to Bose-Einstein statistics. Eventually, if the chemical potential is small enough, you will have a lot of occupation in the lowest lying state. And what you see here is nothing but, I mean,
yeah, it's momentum space, right?
This is real space. This is real space, and this is momentum space. So you see that this is just a two-dimensional sine, basically a sine squared function in both dimensions. It's just the ground state of a non-interacting Bose gas.
Oh, okay.
It's not a localization. It's not an interplay. It's not an interference effect of.
Okay.
Yeah, it's really just.
Thank you.
Yeah.
Oh, thank you. Nice talk. Almost convinced to give up the conventional bosons and go into light. I have
Almost.
a few questions. Thermometry of the photon gas.
Yes.
You rely on the back, so you always have the gas. And if it's so, the total energy obeys a kind of a T⁴ type of relation, like we expect from black body or something. I mean, I just would like to know a little more detail about thermometry of the photon gas.
Okay. It's we have.
I mean, briefly, like a few words only.
Yes, I mean there are many different ways to characterize this, but maybe one I can briefly show here. So we really look for the occupation of the photons on the different energy states that are provided by a system, and the solid lines are 300 Kelvin Bose-Einstein distributions. So you can directly compare the moment or the energy distribution.
So you still rely on the distribution.
Here it relies on
the rate between the modes. Occupation will give you the temperature.
Exactly. So you look at the occupation of that in this method. But in the method I was showing at the end on the fluctuation dissipation relation, it's of course a completely different story. There you measure G2 of 0. Okay. G2 of 0 gives you let me just go there. G2 of 0, of course, is a measure for the number fluctuations. And so G2 will give you the left-hand side of this equation, and you can also study the
extract from the
fluctuations, and this
depending on the temperature.
Yeah, and that's quite interesting because here we don't look at many modes of the system. This is just BEC.
Okay.
So it's just looking into this one fluctuation properties of this one state. It's a little bit like a single mode of a light bulb.
Okay. So if you can quantify so well, what is the law of order parameter construction on the BEC of photons? You know, it is equivalent to what? When I see the BEC being formed and construct as a function of temperature, what is the order parameter dependence with temperature you find?
The order parameter dependence, you mean the something like the condensate fraction?
Condensate and total, yeah.
Condensate fraction. Yeah, I don't have it here on the slides, but you basically see that it follows.
No, I see that you see but what kind of power law obeys? If it is a power law, what kind of thing obeys?
So I
Can I imagine?
I think it scales with a square.
Or something.
So I think from the measurements we did, the condensate fraction scales with T over Tc in a square fashion. So you have no condensate and then goes
And
up.
that goes with the square.
But this has not been like this has not been done in a very quantitative way up to very high condensate fractions. There we are limited. Maybe that still makes atomic Bose gases necessary.
Showing the build-up of the order parameter for a photon BEC. So I think it's very peculiar of the system, in fact.
But it's very close to the prediction for the 2D Bose gas in a harmonic trap, where you get this T over Tc.
Close to harmonic trap in 2D.
Yeah. For the harmonically trapped gas, for the uniform gas, we have not measured actually the. I cannot say what the dependency on T over Tc is.
It would be nice to see if it's really equivalent to a uniform gas, because that's more or less what you claim.
It's a very good suggestion.
And finally, there is effective mass, which must be effective interaction. What is the effective equivalent to scattering length in the case of the photons, in your case?
I mean, the equivalent would be some Kerr-type nonlinearity. That would be a contact interaction.
No, I just want to know if you can make an interpretation of the interaction of those.
I can tell you that interactions are negligibly small in the current setup. Of course, we can implement it by having you need to get photon-photon interactions into the system.
Start to think we can have a equivalent to Feshbach, but not with magnetic field, of course, but with some other things, like controlling. I don't know. I can't predict it, but if we could somehow also introduce this knob.
I think so this is just photons alone, but of course the community working with polaritons, exciton polaritons, I think that was a feeling, or that was maybe the approach, to couple the light strongly to a matter component and make use of the matter being like strongly interacting. For example, you could think of coupling this to Rydberg gases, or some effect that you have actually something like a strong nonlinearity that comes from some matter coupled to it. But directly the photons alone, there's basically no interaction.
Okay, well, I have one more, but there is a coffee break after. So.
There's two more people, but you want to say something about that quickly?
Yeah, I just wanted to ask if anybody has thought about using a nonlinear medium to make the periodic structures, for example, something that may be interesting from strongly correlated physics.
You mean some nonlinearity for the photons within these cavities?
Exactly.
Yes, we're working on it. So, but the idea is to actually have cascaded nonlinear processes to take a photon, send it onto a nonlinear crystal, then double it, half it. Actually, you split the photon, and then convert it back again. And in this process, you can show that a phase is accumulated. And this phase corresponds to some effective interaction. At the moment, it's not even implemented in this microcavity scheme, but it's just essentially a large cavity with a nonlinear crystal. So it's, and you need to basically a doubly resonant cavity. So in one cavity resonant for, let's say, 580 nanometers, and then another fifth mirror that is actually reflective for the infrared light. Yeah.
Hi, Julian. Thank you for the very nice talk. So I have two questions. One, the first part, the other one is more like I want to hear your opinion on the second part. So for the first part, I would like to know if you have an intuitive way of explaining why the cascade is different, like is inverted for wave turbulence and vortex turbulence in 2D. Do you have a clear, like easy way of justifying this difference?
I'm afraid not.
Yeah.
But I'm also really not the expert to ask about vortex turbulence. So I think there are people in the room that have many years of experience and know much better. It's maybe what I can say is in terms of our experimental protocol, of course, we do many things different as compared to the Australia experiment where they have a comb. So they directly inject, of course, vortices. So they directly go to the high K states and then look for the energy propagating in the other direction. In our case, we always start at the lowest possible K state, so the largest length scale. So we shake the box like this, right, very slowly on the fundamental mode. Yeah, I cannot really say. Actually, I think also this all needs to be studied, how it depends on interaction strength, how it depends on the excitation protocol. And I think people now try to use also this not shaking on the lowest mode, but actually a DMD modulation on some higher mode to inject excitations there.
Because actually there are less 2D than you are. If you think about the gas itself, it's like the dynamics of the vortices are 2D, the vortex dynamics, but not the gas itself.
It's true.
So it's
yeah. I think
I
that's
was amazed when I saw the results that the cascade was not inverted in your case. So okay.
Yeah, I mean, from simulations, definitely we can tell, our GPE simulations of the system, we can tell that the most kinetic energy that is in the system is compressible.
Okay.
So there are not many vortices here. Maybe that's an argument for yeah. Yeah. Exactly. It's not crazy, but it's
so gentle.
Crazy, but not super crazy.
Yeah.
Yeah.
And then for the second part, I would like to hear your opinion on what are the advantages of studying superfluid effects in these optical quantum gases compared with the usual ultra-cold gases system you were working with.
I would say you have a way more better, first of all, way more simpler setups. Timescales, of course, of building are completely different. Timescales of the experiment itself are way harder because you have dynamics on a millisecond or microsecond timescale with cold atoms. With photons, everything is picoseconds, nanoseconds. I mean, nanosecond is kind of the slowest timescale. But you have very nice ways of looking at the dynamics and analyzing. I mean, as I said, we can extract temperatures based on spectroscopy. We can look at the fluctuations. We can look at momentum space directly. We can look at real space, and also there are novel effects expected. Actually, superfluidity that is stabilized by dissipative effect. So I think that's a very attractive new direction in the field. That yeah.
Okay, I think that's a great talk, and we should thank, while Marzena is setting up now, we can have the transfer. Let's thank Julian for a wonderful talk. And so Marzena Szymanska from UCL will be telling us about exciton polariton condensates. And unless the title has changed, it
close. It doesn't. Okay, I have to be close here. Okay, so I'd like to thank the organizers for kind invitation. It's an excellent conference and very nice place. And it's the first time for me in Brazil and in South America altogether. So I will talk about novel non-equilibrium phenomena in quantum fluids of light. So I would like to start. I would like to start by acknowledging my group in UCL, and especially Alex Ferrier, Paulo Comeron, and Cristobal Ledo Veloso, whose work I'll be presenting here. And parts of the work were done in collaboration with either Jacobo Carusotto or Michał Matuszewski. And I would like to acknowledge our funding from EPSRC and Quantera Network. So we already heard about quantum fluids of light in the previous talk, but also yesterday mentioned by several speakers. So basically, the motivation of my talk and motivation of what we've been working in our group is that in the last decade or last 2 decades even, there has been a great experimental progress in creating systems where photons via interactions with some matter component are firstly made massive and secondly are made to interact. So if you turn photons to massive interacting particles, they behave very much the same as cold atoms or some other particles in solid state, and you can create quantum fluids of photons, so quantum fluids of light. And in the community or in our group, we study a wide range of phenomena. The photonic platforms are allowing us to study non-equilibrium phase transitions, critical phenomena, non-equilibrium superfluidity, topological transitions, and defects. So this is the kind of part which is relevant for that workshop, because as you can imagine, if you want to trap photons into a box, you have to trap it at least in one direction. So you cannot create a trapped photonic systems which are 3-dimensional. They will be 2-dimensional. You can make them 1-dimensional, 0-dimensional, but not 3-dimensional. So we are intrinsically low-dimensional with photonic systems. And then following in the footstep of cold atoms, and motivated by the same kind of ideas as in cold atoms, we know that cold atoms first created a condensate and superfluidity, but then moved to lattices. So the same in the last 5-10 years, the new era is emerging of quantum solids of light, where now instead of just a quantum fluid in 2-dimensional, in 1 dimension, lattice potentials are created for photons. So this is done in majority of experiments are based on micropillars, where physically one is edging a system in a way that your microcavity now becomes 0-dimensional. So here is a microcavity. Here you trap your photons, and then the photons can hop. You can create rings, you can create lattices. This is, for example, an example of polariton graphene. But polaritons are not the only systems. There are also similar directions in the case of circuit KD. So circuit KD lattices for photons have also been created. My talk will mainly focus on that aspect, since this is the topic of this conference, but I will also discuss one project in connection with lattices. You have to be closer to the source. So what are we really talking about? So in case of photons, as I mentioned already, you need to trap them in some container, which can be a real cavity, which can be a microcavity, which can, I mean, there are various waveguides, there are various ways of trapping photons. But whatever you do, you can never create an ideal mirror for photons. There will be always some dissipation, so the photons will always decay. And in order to sustain some steady state in the system, you need to drive it from the other side. So you are really intrinsically out of equilibrium. You are intrinsically at least 2-dimensional, and you are intrinsically out of equilibrium. So there are the various systems which has been considered today. I will mainly focus on polaritons, but there are also photon BECs, which we heard in the previous talk. There are circuit KD systems, which I won't talk about today, but we also have works on circuit KD. There are atoms in cavities, and there are probably more platforms. So the field is quite large. It's not just polaritons. And although I'll be basing, you have to focus on something. So of course, we'll be focusing on polaritons, but everything which I'm going to say will equally apply to other platforms. So what is the question which which I need to ask is, so firstly, in our community, the first focus was just to create a condensate. Yeah, so probably similarly as in cold atoms. We wanted a BEC or we wanted a BKT, we wanted an equilibrium condensate. But once that has been achieved and the box has been ticked, people start wondering, okay, is it just a repetition of cold atoms, or can we actually use the non-equilibrium nature? Can we use the fact that the system is driven to create some new phases? So we don't want to just be a little bit out of equilibrium. We really want to create a non-trivial phases which are intrinsic to non-equilibrium physics. So my question is, can we engineer such phases? And the outline of my talk is the following. I will, since here the organizers are very generous with time, it's probably the only conference which allows one hour. So I hope to be able to cover all of these very interesting non-equilibrium examples, which can be realized in quantum fluids of light and in particular polaritons. So I will start from discussing what I call it unconventional BKT. So where a multi-component nature of polariton system combined with non-equilibrium nature leads to a kind of a new state where algebraic order can actually coexist with some free vortices, which is something which has not been seen before. Then I move to another topic where now also this is maybe more specific to polariton system than anything else. What I'm going to talk about is that our polaritons always coexist with other particles. It's not like cold atoms, where cold atoms are completely isolated in this nice harmonic trap from everything else. Here polaritons are sitting in a solid state material, in a mess of other things, and in particular in a mess of excitons. So excitons are not condensed, so you're coupling, but of course the excitons and polaritons interact, so you're creating a superfluid, a coherent fluid, a quantum fluid coupled to a classical fluid. And such a reservoir dynamics actually leads to something which is equivalent to attractive interactions in the system, so it leads to modulational instability. And we can see both in the experiments and in theory, like that, two critical points. We see a second and first order phase transitions, and there is quite a lot of analogies to active matter and biological system with that. So that's quite an interesting example, because polaritons allow us to kind of mix classical physics and quantum physics in the same box. Finally, the first example which I will discuss is the kind of the most out of equilibrium feature you can think of in this driven dissipative condensate, the Kadar-Parisi-Zhang equation and KPZ physics. So I will show that because of drive and dissipation in the system, and in particular because of nonlinear drive, the linear drive and dissipation will not work. But if you have nonlinear drive, this leads to the phase dynamics, which is very different to the one if you have a closed system. So basically, I will show that the phase of a driven condensate obeys KPZ equation, and KPZ equation is a new universality class, very popular again in classical system, in biological system, for example, and crystal growth, and quite a number of others. And however, unlike in these other examples which exist in nature, here the phase is compact, and this is the only, at least to my knowledge, but of course, correct me if I'm wrong, this is the only example when you have a KPZ for a compact variable. So that's something really interesting, which opens a new area of research, how vortices and how topological defects connected with compactness of the phase compete with the KPZ order, and whether at all you can see KPZ in that for the compact variable. So that's an open question still, and an ongoing research. And finally, hopefully I'll have time to that, is that we can also put these condensates in lattices. As I mentioned earlier, you can, for example, etch micropillars in cavities. And in particular, what has been done is graphene, and even in more particular is strain graphene. So strain graphene, of course, leads to artificial magnetic fields, artificial gauge fields. But here we'll be looking at putting a condensate in such a graphene. So I'm not going towards Bose-Hubbard. Obviously, this is not a conference about strongly correlated systems. This is a conference about superfluids. So I'll be just putting my superfluid into such a strain graphene lattice, and that would mean that I will have an interesting condensation without putting any external rotation. My condensate will will rotate, will condense into the lowest Landau level and will form vortex array. And because it's an artificial gain field without direction, the system will be spontaneously breaking time reversal symmetry, for example. Okay, so let's start with the first topic. So we already, I probably could almost skip it because we had a very nice introduction on BKT from in the previous talk, but just to set the ground kind of slower, we know that in 2 dimensions, when you go from order to disorder or superfluid to normal state, this is done not via BEC mechanism, but via BKT mechanism, which means that a destruction of coherence is generated via proliferation of vortices, or if you go to another direction, appearance of coherence is connected with binding of vortices. Yeah, so this is a cartoon from the 2016 Nobel Prize. So, of course, equilibrium BKT has been seen in ultra-cold atoms. We heard about it just a minute ago, and in electronic systems. It was not seen in any photonic systems, but the photonic systems are special. So they are special because they allow access not only to spatial coherence, but they allow access to temporal coherence. So temporal coherence in the BKT was not measured before in any other system because it's not possible in cold atoms or electronic systems. So there has been a huge effort in the community, and I will talk about the final experiments, 2017, by Daniele Sanvito group and with our theoretical collaboration, where this equilibrium BKT has been achieved. And what has been seen, basically, it was a very clear, so how can you see whether you have a BKT? Well, you should have an algebraic decay of correlation in your order state, and then this should jump to exponential decay of correlation in the disorder state. And that's what has been seen. This is a G1, experimental G1 in space, and also they see the same in time. So this is perhaps not appreciated, that if you really have an equilibrium BKT, you should have algebraic decay in both, and they should be equal. Yeah, so if you really have equilibrium BKT, the spatial and temporal exponents should be the same and should be smaller than 1/4. And this is what has been observed in this experiment. Of course, this experiment cannot measure a single shot, so they could not see the pairing and unpairing of vortices, but theoretically we could tune our parameters to exactly reproduce the G1 in space and time, so we were pretty sure we were in the right place, and then look at a single shot in numerics, and we could see that whenever we have exponential decay of coherence, this corresponds to presence of free vortices and anti-vortices black, and this is a phase profile. Black and red is vortex, anti-vortex, and wherever you have algebraic decay, either you had pair vortices or there was no vortices at all. Yeah, so we were kind of convinced that that was a BKT. Okay, so I was going to talk about non-equilibrium, not equilibrium. That's why I've just flashed it as an introduction. And so in closed system, as I already said, this exponent is given just by temperature over density, and is smaller than 1/4. Yeah, as you heard from the previous talk, because it's connected with the universal jump. However, what happens if we don't have equilibrium? If we don't have equilibrium, if the system is driven dissipative, the structure of collective mode is changed, and it has been shown by us ages ago, in our high times already, that is still a power law. So the drive and dissipation is actually not killing the main feature, is still a power law. But firstly, there is a mismatch between time and space. And secondly, there is no a priori reason for that to be an upper bound. And these earlier experiments, which the ones which were not yet able to show equilibrium, indeed were able to so these are the earlier experiments before Daniele Sanvito experiments. Indeed, they show that you have algebraic decay of coherence with an exponent which was exceeding 1/4. So this is an experimental realization. It's about up to 1.2, and these are our numerical calculations. So this prediction is based on Keldysh field theory. Is of course approximate. It's analytical, but it's approximate. But you can run exact numerics, and then you can actually show that there is no upper limit, or at least the upper limit is not 1/4. It can be much larger as in experiment. So what that show us, well, this is just, I'm just giving an introduction. This is not a new work, but what is shown that if you have a drive and dissipation, you create an overshaken superfluid. What it means is that you can put much more collective excitations and obtain a much larger exponent of the power law decay before you proliferate vortices and you destroy the coherence. Yes, so you remember vortices means no coherence, means exponential decay. No vortices means power law decay and with an exponent, but this exponent will depend on temperature in equilibrium system, or here will depend, on some noise level. And in equilibrium, you cannot have such large exponents because you will proliferate vortices. Here, we do not proliferate vortices, but we can have much larger exponents. So it's a kind of overshaking of superfluid. So faster decay possible than in equilibrium upper limit. Okay, but that's still quite analogous. What's the difference? I mean, the only difference is that you can have like a larger, faster decay of spatial and temporal coherence and equilibrium, but everything else is the same. Can you actually generate something more different? So we start looking at a system which is very much out of equilibrium. Yes. So after ticking a box of obtaining an equilibrium BKT, people start looking at systems which are actually very much out of equilibrium. And there is a special configuration of polarity on condensates, which is really very much out of equilibrium. And this is OPO. So this is optical parametric oscillator. In polarity on condensates, I won't go into the details of semiconductors, but you can drive system very differently. You can drive it incoherently, you can drive it coherently, and you can drive it parametrically. There are 3 different ways. So the parametric driving, so the OPO, means that you drive your system with a laser at a so-called magic angle, and then you have stimulated scattering to the kind of bottom of the polarity on dispersion, and here to the idler state. So you have a signal and idler. So you would think, well, it's very non-thermal. I mean, there is no thermalization. However, you have still a free phase in the system. So the signal and idler are not locked to the pump. So the difference between signal and idler phase is a free phase. Your Hamiltonian is completely invariant under that. And so when the condensation happens, you have spontaneous Yuan symmetry breaking. And of course, this leads to gapless and diffusive Golson mode. So this is spontaneous condensation, although the system is first the multi-component. You have signal, pump, and idler. You have like 3 condensates in your system, but you have 1 free phase. So its Yuan symmetry is the same as any other condensation. So that's just a Hamiltonian exciton photons with some interactions between excitons, and then drive and dissipation. So what happens here now? So now my system is a little more complicated than just a single component condensate. It has signal, pump, and idler, and it has excitonic and photonic part. Pump is not relevant because pump is something coming from outside. So you have signal and idler, excitonic and photonic. It's a 4-component condensate. So in the kind of recently with Gala and Paolo, we used to we looked at individually at the components and the phase transition, how it's taking place in different components. So here is average number of vortices as a function of pump power. I wanted to point out that here we don't have a temperature. So the critical parameter which drives the transition is the density of polaritons. So pump power. Yeah, if you drive stronger, you have more polaritons. If you drive weaker, you have less polaritons. And then of course you are looking at the steady state. So this is a pump power, not in time. It's a pump power. You fix your pump power, you reach a steady state, then you may choose another pump power, you reach a steady state, and you can look at the phase diagrams as a function of density in some sense. So so now when you in this parametric process, photonic signal, excitonic signal, and excitonic idler are more or less of the same density, but photonic idler is very weak. I mean, that's I won't go into details why, but this is just a kind of microscopics of the OPO process in semiconductors. So we have 3. You have a multi-component fluid which has 3 components which are of large density and 1 component which is a very small density. So it's not really that obvious what's going to happen. So we look what's going to happen, and we see that there is a kink in the average number of vortices at the same point for all components. Yeah, so the phase transition is happening at the same time for all, or the same pump power for all components. And when we look at the G1 and the power law coefficients of that G1, we see that it's almost identical for all components. So these components are really very much locked. But when you look at absolute value, number of vortices, you see that in the idler, there are many more vortices than in the other components because the idler has much lower density. So in some sense, it's a little, you already see that there is a little contradiction, because at the same time, you have a G1 which would be identical for all of these components, but the number of vortices is different. So you see a situation where you have algebraic decay, but still the number of vortices, the average number of vortices is quite large. So it looks like the collective modes between these components, which set the algebraic decay exponents, are locked in the OPO process, but the vortices, which are local defects, are actually quite independent between components. So we start looking at the correlation. So if I now show here, so let's look at what these vortices are doing. Let's look. So if I take the kind of more conventional part of this multi-component superfluid here, and I look at the correlation between vortices here, so what it means, this is a density correlation between vortices, which means that what happens if I have a vortex at 0? What is probability of having an anti-vortex as a function of a distance? And this red line here is the BKT phase transition. So you can see that above BKT, if I happen to have a vortex at 0, my probability of having anti-vortex is very localized here. I have a tightly bound vortex anti-vortex pair. If I go very far away, it's 0. Yes, I don't have any free vortices. If I am below the BKT transition, of course, I have some degree of pairing. So I have these two peaks, but as I go away, I always have an offset. So it means that I have many free vortices in the system. This is for the signal. But when I look for the idler, even if I go above the BKT and I look at these correlations, I see obviously I have some pairing, but I also have still quite a number of free vortices on average in the system. So well, it's not really very common. Yeah, I mean, it's actually we're not aware of any example where you could see an algebraic decay, but still see a kind of vorticity in the system. So looking at, I mean, these are just all correlations, and it's difficult to imagine how it looks. So I plotted a single shot. This is a single shot phase profile for the photonic signal and photonic idler. So if you just look at the kind of colors here, you see that between vortices, the phase is more or less following the same pattern between photonic signal and photonic idler. But unlike in photonic signal, I have no vortices whatsoever. In photonic idler, I see some vortex-anti-vortex pairs, and even from time to time, free vortices. So in some sense, the parametric process connected with non-equilibrium and connected with multi-component nature is locking the kind of phase modes, the sound modes, but because vortices are kind of free between the components, I could have some vortices in the idler and not in the signal. So I'm creating a very interesting superfluid. I'm creating a superfluid which has algebraic decay of coherence, but still some vortices. Yeah, so something really not seen before. Okay, the second topic I mentioned, which again is connected with non-equilibrium physics, is the fact that sometimes in these experiments they can pump in one part of the sample, and then the photon fluid, the polariton fluid is flowing away and is forming a condensate away from the excitation spot. Then you can only deal with polaritons, but this is not always possible. I will not go into details why and in which setups. I mean, there are different samples, there are different configurations of the experiment. So sometimes it's possible to pump in one place and have your condensate in another place, so you only have polaritons. Sometimes this is not possible, so you pump in the same place as the condensation forms, uniforms. So it means, and you always pump excitons first. So you have excitons coexisting with polaritons, and you cannot avoid that, yeah, in some cases. So that, of course, this will influence everything because your kind of coherent polariton field given by psi here will couple to a classical field, dynamical classical field of excitons. It will feed from this excitonic reservoir, but you will also have a dynamics of that excitonic reservoir. So these are the equations we are describing the situation. Yes, coherent polariton field coupled to this excitonic reservoir, feed from this excitonic reservoir, and an excitonic reservoir itself having its dynamics. And that is the kind of more common situation in a not good quality sample. So what happens then is that if you have a weak drive, obviously you have some disorder phase, there is no condensation. But as you increase your drive, so you have more particles in the system, you start condensing, but you start condensing into inhomogeneous superfluid. So the vortices will be pushed away to these low density areas, and then here you form a condensate. And then over a sudden, you increase your pump power and you jump to a completely uniform, beautiful condensate. So we looked with Michał Matuszewski at the nature of this transition between this non-uniform condensate and the uniform condensate, and we find that it's really a first order phase transition. It's connected with phase separation, and there is a sudden jump of vortices and multi-stability, and that's of course different to BKT. So what I'm basing this on, so this is just a single shot just to show you by eyes what is happening. Sorry, it's not moving for. But if you average, obviously, if you run hundreds, thousands of those realizations, we can get a statistic. So as for different densities, we calculate the number of vortices, we calculate the density, we calculate the correlation length, and you see that at the moment when these puddles start forming, like there is really a sudden jump. It's not a smooth transition. It's you have this non-uniform condensate, and then over a sudden it turns into a uniform condensate. It's not that the puddles are growing in size slowly and continuously. No, you have quite small puddles, and then over a sudden a completely uniform condensate. So there is a very sharp transition in number of vortices, in density, in correlation length at that point. And then if we look at around that point, this is really around that point, 1.326, I mean, there's almost no change in pump power. It's really very narrow here. And then we see that depending on the realization, sometimes we are in the uniform state or we are not in the non-uniform state. So it has bistability. So this is connected with the finite size. Of course, our system is a finite size. If we went to a completely infinite system, we will lose bistability. But in the finite size, the first order phase transition in a finite size system corresponds to bistability in the region around that, around the critical point. So this is another evidence that it's a first order phase transition. So, and that's something also reminiscent of a first order phase transition is a coexistence of phases. So we drive the system uniformly. There is nothing really giving the circle here. The drive is absolutely uniform in the box. There is periodic boundary condition. There is nothing giving you a circle. And yet we observe if you tune the pump power to the critical point, we observe cases where there is coexistence of the uniform condensate here. And in the circle, you have this non-uniform modulational instability kind of phase with vortices pushed here to the side. So this is a phase. This is the amplitude with vortices put there. So why? So that's the first order phase transition. But when I look earlier, so this transition from non-uniform to uniform here is first order. But if I looked earlier in the pump power, I can see that when I move from completely disordered phase to this partial order in these puddles, I see that this is happening via BKT. So my puddles start forming, my vortices start forming bound pairs, then they annihilate, and finally I have no vortices in these puddles here. So I have coexistence of first BKT and first order phase transition. So in KTP, I discussed quite a lot about that with Letizia Cugangiolo, who is an expert on classical BKT and even in biological and active matter systems. So our model is analogous to Wiesek model of flocking of self-propelled particles. So this means if you want to look at how birds or how fish order, so the complete disorder, when you go from complete disorder to an order phase of fish or birds, it's happening via pattern formation. So first they form these coherent puddles, and then the coherent puddles merge into the fully coherent state. So this is very analogous. And also coexistence of first order and BKT has been seen in XY models where the interactions is theta dependent. So if you have XY model which is just theta with constant interaction, you will not see it. But if you make theta dependent, then you can also see that. And that's also a description of a lot of active matter systems. And we were also pointed out by actually referees of this paper that similar things can happen in Griffin phase in dilute Ising ferromagnets, where partial order in each of these mutually disconnected islands first happen and then it merges into the one state. So it's a kind of an interesting laboratory, because this is very, very well tuned to study this type of phenomena, which is perhaps a little more difficult to study in other systems. Okay, so now I'm moving to the kind of most out of equilibrium realization in that system, so to the KPZ. So why KPZ is interesting? Well, apparently it's a very nice mathematical theory. A Fields Medal was given for a solution of KPZ equation in the UK in 2014. And as I briefly mentioned already, it's a universality class for really extremely wide range of non-equilibrium phenomena in one dimension. Surface growth, burning paper, a lot of biological systems, and many more. But so far, to date, there is no clear experimental realization of KPZ in 2D. Not to mention that our system is also compact, but even in 2D, there are not really like a very clear experimental realization. So people thought that polaritons could be, or I don't know, some other, not only polaritons, it could be also other condensates with drive and dissipation, who could be a good laboratory to study that. So what's KPZ? So if I take my condensate and I eliminate, so as you know, in the condensate, we have a phase fluctuation which are gapless, and we have amplitude fluctuation which are gapped. So gapped fluctuation can be integrated out to second order, and I can obtain an effective theory just for phase fluctuation, because those are gapless, I cannot integrate them out. And I can do that for closed system too. And if I do that for closed system, I obtain the usual diffusion equation for the phase. So if you just for a moment forget about these terms underlined in pink, here this will be your phase equation for a normal condensate, so not driven dissipative condensate, and this will fall into the universality class of XY model and give you algebraic decay in 2D. However, if you have drive and dissipation, especially nonlinear drive or nonlinear dissipation, you generate additional terms. So terms which are proportional to the square of the derivative term. So this is a KPZ nonlinearity, which change things dramatically if you add those terms. So how it changes? Well, you don't have algebraic decay anymore. If you calculate correlations at large distances in 2 dimensions, you have stretch exponential decay with this characteristic KPZ exponent. However, if you don't include compactness of the phase, if you just assume that psi is not compact, then superfluidity survives. So you could have a nice state, again, new state of matter, where there is no algebraic decay, but you have superfluidity. So that's something which has not been seen before. So again, a lot of excitement, but it was that was actually proposed by Altman and Sebastian Diel and Lukas Sieberer. But when people start looking in details about polaritons, it actually was quite pessimistic, because if you just take the usual setup of incoherently isotropic microcavity in 2D, unfortunately, KPZ order cannot be seen. And it cannot be seen for 2 reasons. So if you make a system very large, it turns out that the system will be killed by vortices. I will explain in a moment why. And you see exponential decay of correlation. If you make a system smaller, to avoid that, because these vortices will appear at larger length scales, then your KPZ length scale will be too large for your system, and you only see power law decay of correlation with system size, as what I already shown. Yes, so there are experiments. There are lots of experiments by now showing algebraic decay of correlations in the in polaritons. There were no experiments showing KPZ till very recently, but this experiment of Jacqueline Bloch experiments, but in 1D, but it also has a special caveat. It's on a lattice. I will mention later why that was possible, but normally you see power law decay. So why is that? Why the vortices are so bad? So if you now again Sieberer, if you take your KPZ equation and you calculate vortex interactions in the KPZ equation, you will arrive at this approximate formula, which will have a term equivalent to the attractive interaction in XY model. Yeah, so that's why you have BKT transition, because interaction between vortex and anti-vortex is attractive, so they come together and they annihilate. However, if you have a KPZ equation, then you get this extra term, which can be negative or it can be positive. And the nice thing here is that it depends on anisotropy of the system. So if the system is fully isotropic, so the same in X and Y direction in our 2 dimension, then unfortunately this term is negative. So I mean, this positive, and then you have a minus sign, so negative overall. So for isotropic system, the interaction become repulsive at some length scale. Yeah, so this is attractive, this is repulsive, and this dominates at large scales, this dominates at small scales. So if you go to larger system, finally you have repulsive interaction between vortex and anti-vortex pairs. So if from noise, like you can always have some vorticity in the system, they will not be able to annihilate. So in a kind of non-equilibrium steady state, you will always have free vortices in the system, and they will kill superfluidity. So the fact that this sign is wrong is kind of problematic. However, if the system is very anisotropic, then this, and by very anisotropic, so I probably should mention before I go to the next slide. So by anisotropic or isotropic, I mean you have lambda x and lambda y. You can make them equal, and then the system is isotropic, or you can make them not equal, and the system is then anisotropic. And in particular, if you make lambda x equals to minus lambda y, this is strongly anisotropic. That's what people call strongly anisotropic systems. So just to remember that. And then the physics is very different. If the system is isotropic, the KPZ terms are important. If the system is strongly anisotropic, so it has one is minus the other, in RG, these terms can be eliminated, so you don't really have a KPZ, but at the same time, the vortices are actually attractive. Yeah. So, so if I now, sorry, so to explain why it became problematic to see KPZ in polaritons, to kind of thinking naively, just taking a 2-dimensional isotropic system, is because I have this negative sign here. So my vortices will repel each other, so they will not form, you will not have a BKT transition. You will always have free vortices, which will kill your coherence. You can change the sign, and you can make plus here, but then the terms connected with KPZ will get eliminated in the RG analysis, and you are back to the BKT. But it's still interesting because you'll be back to BKT with enhanced interactions. Yeah, so it's not just a BKT. If you take KPZ, anisotropic KPZ, you will have BKT with stronger interaction between vortex anti-vortex pairs. Okay, so then this first analytical analysis got. There are lots of approximation performed. Some of these approximation people didn't really believe, and that maybe this is all not right. So of course there is no harm in just taking your KPZ equation and solving it exactly numerically, and that's what we did. So if you take an isotropic case and you run this is like a typical example of a single shot, you see millions of vortices. Yeah, for convenience, I will zoom. This is our simulation box, but you can of course zoom it, and you see lots of vortices. Of course, no hope for any KPZ or anything else. I mean, this is just exponential decay of coherence. If you just change a sign, so it's quite a nice exercise. This numerics was done by a master student, and it's very exciting because the only thing you do in your program, you just change plus to minus or minus to plus, and you go between these two cases, and you see that if the system is strongly anisotropic, you get a beautiful coherence, and there is no vortices in the system. Yeah, just by changing the sign. So this is a single shot. So either no vortices or really very nicely bound vortex anti-vortex pairs. So now, of course, just single shot doesn't mean much. You have to do statistics. So if you run over hundreds or up to 1,000 realization, we see that this is a phase ordering in time. We start from some initial conditions which has a lot of vortices, and we see that as you cross from disorder, so this is a phase ordering of the rapid quench, yeah, the usual one. You go from disorder to ordered, and you see what's happening. So, and this is as I'm increasing my nonlinearity, my KPZ nonlinearity. So as I increase my nonlinearity, of course, I have more vortices, and you see that I'm just saturating. Yeah, so this is my steady state. Really, I really have vortices in the system. Yeah, so the kind of prediction was correct. And moreover, the dots are our numerics. The lines are, you can always take this formula predicted by Lucas Sieberer, and you can derive your equations for the behavior of the vortices. Yeah, you can predict how the phase, if you have interaction between vortices, you can predict the phase ordering. So the lines are basically the analytics coming from that formula. So it really fits beautifully. So whatever approximation were done there were correct for that system. And then when you take a strongly anisotropic case, we see that as predicted by RG, the terms become irrelevant, and you really see the nice, beautiful phase ordering to zero. With I don't want to go to that, but with exponent, which is not exactly the XY exponent, it differs a bit. This is probably because you have these enhanced interactions as opposed to the XY. Okay, so in some sense, my prediction is pessimistic. Yes, either KPZ order is destroyed by vortices, or you have universal behavior and XY model. So KPZ is not really relevant for polariton. So that one could conclude, but that's not the case, and because you don't have to be either completely isotropic or completely anisotropic. Yes, so you can just be somewhere in between. Maybe adding some anisotropy, but not strong anisotropy, might actually help to beat those scales. We have to beat scales. Yeah, so obviously for completely infinite system, I generate these free vortices, but I just want to have a system of the size that my KPZ can show up before the length scale of vortices kicks in. So in homogeneous system, in isotropic system, that's not possible. That the vortices will always show up before the KPZ, but maybe if I add some anisotropy, it will be possible. So how can you add anisotropy? It's not really easy to add anisotropy in the growth, but we have our old OPO, yeah, which I already explained in the first project. So because if you OPO, you drive the system at an angle. So your dispersion is different in the direction of the drive than perpendicular to the drive. Yeah, you have some anisotropy in the system induced by that. And the calculations are much more complicated, but they're in the same spirit. So you write down your equation for Signar, Pump, and Idler, and then you have 6 variables. Yeah, you have 3 amplitude modes and 3 phase modes. There is only one gapless mode, so you can integrate out the 5 gapped modes and obtain equation only for the gapless mode, because the gapless mode gives you the low energy behavior of the system, and it happens to be of the KPZ form. So that's what we did in that paper. And now the coefficients of dx, dy, lambda x, lambda y are very complicated functions of microscopic parameters, but they're analytical. Analytical in a way that they take like 5 pages of Mathematica, but still they're analytical. So you can connect the microscopics with of the OPO with the phenomenology of KPZ. And what happens is here, as I increase my drive, so this line corresponds to increasing drive for different detuning. So this is detuning between exciton and photon. It's just, it's technicality, but it can help you to be in a different place of the phase diagram. They can always detune the exciton energy with respect to photon energy. And interesting thing happened is that as you increase the drive, you change your anisotropy and you change the noise levels. You travel along these lines. And completely counterintuitively is that if you increase, by increasing the drive, we move from non-equilibrium to equilibrium fixed point. So that's counterintuitive. Yeah, by increasing the drive, you think you become more out of equilibrium, but actually not in this case. In this case, by increasing the drive, I become more equilibrium than a smaller drive. So if I really go very large with the drive, I increase my anisotropy to the extent that I'm back to the XY model fixed point, and I can just go between algebraic order and no order via the usual BKT transition. But if I am here, so I'm kind of weak with drive, but I can still be anisotropic. Weak drive gives me weak anisotropy. I'm in the KPZ state. And moreover, I will not explain that. This is technical. But moreover, what we found is as a function of pump power, we found that G is a very important parameter. It sets the length scale of your KPZ physics. So if G is larger than 1, then you should see this KPZ stretch exponential decay of coherence at all distances. So it's best to be in the regime where G is larger than 1. And we found that this weak anisotropy gives us quite narrow, but still a realistic range of pump powers where the KPZ should be seen in the OPO. So again, that was done using some Keldysh field theory with some approximations. You know, experimentalists don't believe in approximations. You really have to do your work properly. So you have to take an experimental condition and run numerics exactly to be sure that you don't have any other artifacts in your system which may wash out this interesting behavior. So that's what we did. We did truncated Wigner simulation for this KPZ, and what we found is basically a confirmation of what Keldysh field theory predicted. So as you increase pump power, this is a phase diagram. You obtain an OPO threshold. There is also an upper threshold. So there's like a reentrance phase diagram in the OPO case. If you drive too strongly, you also kill your condensate. If you drive too weakly, you don't have a condensate. So you have this phase diagram of and the condensate density is given by this yellow line. And from this Keldysh field theory, we know more or less when our G becomes larger than 1. It's where the red line is here. Then we calculate G1 from numerics, and we see something which you already by eye, so you can see that something is happening. So if I take a red line here, I have quite a large condensate fraction. I almost have the largest possible condensate. If I take this green line here, I don't have a much condensation, although it's already quite above the BKT. And then, so if I take this 2 and I plot G1 has a power law decay, but in fact is so strong that it's almost constant. Yeah, my condensate density is already, my coherence is already so strong that power law, no power law is almost 1. It's almost pure condensate. Here, when I take the red line, I can see that my condensate is even stronger. The density is even larger. So my coherence should be even stronger than for these 2 cases. But yet you see it's much weaker, and it decays that way. And when we feed the decay of coherence with this stretch exponential form, we get the coefficient 0.39, whereas the universal is 0.37. So we were pretty sure that that's KPZ, because I mean it's really very close, and also you know it's quite by eyes. I mean, even if you don't believe fittings, you see that something is happening. It cannot be that a condensate which is much stronger over a sudden gives you a much lower coherence than a condensate which is weaker. So we kind of announce a victory that KPZ is within experimental reach, although the range of parameters is not very wide, but still you can try to do that. And we are in collaboration with Sheffield experiment to try to realize that in the OPO. Of course, the referee never gives you easy life. So they were saying, okay, fine, but you know, fitting G1, you can fit anything. something, a smoking gun for KPZ. I'm not a KPZ expert, but apparently a smoking gun for KPZ is if you see distribution of phase fluctuation between reference time T0 and T0 plus delta T, having this universal distribution found by Halpin and Heli in that paper. And what it should be, so this predicted KPZ stationary distribution in 2 dimensions is the red line, whereas for a Gaussian fluctuation is the yellow line. Yeah, so we were asked to compare. So we calculated that phase fluctuations, and the one which comes from our data is the blue. Yeah, so after that, the referee was convinced that indeed, I mean, this is really very hard to achieve unless you have a KPZ. So that was another smoking gun for that. Of course, you could ask a question, is it really a steady state, or maybe we are catching some transient? Maybe these vortices will be there and will kill our KPZ despite this nice condition, but we are just not there yet in time. So in our numerics, we usually start from the condensed state, and then we add noise and we propagate. But it's a driven dissipative system. It shouldn't matter from what initial condition we start. So in order to prove that we don't have a vortices in a steady state, we started from a completely noisy state with 10 to the 2 vortices, and then we run the numerics for a long time, looking at phase ordering, and that is a massive time. So Alex had other things to do, and every group meeting, we have a group meeting once a week, he was reporting that 1 vortex anti-vortex per decade. So it took 1 week of real time for 1 vortex anti-vortex. This is a half a year of simulations taking whole UCL cluster. I don't know whether it was worth it. You can tell me, to spend to use so much resources, but we have proven that number of vortices eventually decay below 1 pair. So it really means that we have a KPZ which is a steady state, which is not a transient. And it's also interesting, something maybe to look later, that this it gives an exponent which was a bit different than what is expected from the XY universality. One could study further. Okay, so to summarize that story is that KPZ scaling is, strictly speaking, not possible for compact fields in isotropic 2D systems in thermodynamic limit in the steady state. There are always free vortices. This is still holds. But it could be possible only in finite system. Yeah, our system is finite, or as a transient. But still, if you take isotropic system, it's still, you cannot satisfy condition because the length scale for vortices will be smaller than KPZ. However, we show that it's possible for weakly anisotropic systems, such as, for example, the OPO. And also, I have to point out that Jacqueline Bloch realized also in the lattice system. So if you have a KPZ on a lattice, then also the vortex fluctuations somehow are suppressed because of discreteness of the problem, and apparently also KPZ can be seen. So that has been, I learned about it from Anna Minguzzi at the Bonn conference, which Axel organized. So maybe in the kind of last. Yes, so just briefly, because this is perhaps less of interest to this community, but just briefly that also these quantum fluids can be put in lattices. It's possible to engineer a graphene, a polariton graphene. It's possible to engineer strain graphene because you could edge those pillars in a way that there is a dependence in space for the distance. And this, if you calculate the band structure of strain graphene, it corresponds to a band structure of a system with magnetic field, and you have Landau levels. Just that artificial magnetic field has no direction, so you have on this side, you have a positive, and this side, negative magnetic field, for example. So this has been realized. It has been realized experimentally and showed the spectra by Alberto Amo in Lille. But what happens if we put condensate into this? So as I said in the introduction, I'm not interested in Bose-Hubbard model yet because they are not in that regime. They are not yet in the regime of large U. They are in the regime of a small u. So you have a still quantum fluid, but in this band structure. So then again, with Cristobal, we did my PhD student who is now in Canada, we did simulations. You can drive your system with some uniform, but let's say this was a Gaussian pump, then you generate a condensate, a uniform condensate. If you increase the size of your drive, but we don't put any rotation externally, not at all. Yeah, we just drive the system uniformly. Then we see that if the drive is over a larger area, the condensation happens with the vortex. There is a rotation, and then if we drive it even in a larger area, we see vortex lattices forming. Yeah, so there is no, I have to say, there is no magnetic field. There is only artificial magnetic field in the system, and there is no rotation. There is only this artificial rotation, which comes from the band structure equivalent to strain graphene. And we create a condensate, or we create a superfluid, which looks like if we took cold atoms and start rotating a trap, or if you took a helium and start rotating a trap. Yeah, so the system spontaneously condenses into this Landau level. And the difference between a real magnetic field or real rotation will have a direction. Here, we don't really have a direction. So one round will give us rotation in one direction, another round will give us rotation in another direction. So the system is spontaneously breaking valid symmetry, and this is equivalent to spontaneous time reversal symmetry breaking. And if we drive on an even larger scale, so if we take even, I mean, this is the size of the system. You can see the underlying micropillars. Even we saw cases where the system phase separates and is condensing in the lattice, rotating in one direction in one part of the sample, and it's rotating in another direction in the other part of the sample. So it's quite interesting. And experimentalists have not yet seen that. They have seen the Landau level and formation, but not yet a condensation to the Landau level because of the excitonic reservoir and other dirt of the semiconductor. But that's something they're working on, and hopefully this can be seen. So I just conclude that, well, if I have to answer the question, are there any interesting phases which are strictly out of equilibrium, which can be possible in these quantum fluids of light? I guess I convinced you that yes, I gave you 4 examples, and basically that's the conclusion that I discussed. These four topics which are intrinsically connected with the driven dissipative nature of polariton fluids, and some of them are intrinsic to polaritons, like this one, but these 3 are not really. Yeah, so they can also be seen in photonic condensate, circuit Kidd systems, any other driven dissipative light matter systems. Thank you.
Okay, thank you, Marzena, for an extensive talk. I'll start with the question.
So being no expert, let me ask the following. In your numerical analysis to determine the stretched exponential, there was only a quite tiny interval where you could fit. And that's also the same in the experiment of Jacqueline Bloch. So I'm wondering what determines the size of the interval where you can really find such a stretched exponential? What determines the upper boundary? What determines the lower boundary?
Yes, so it's not so tiny for this, because this is a logarithmic scale. Yes, I maybe should point out, I mean, it's a logarithmic scale. So this is 100. Okay, maybe do I have a linear?
Not even a factor 10,
okay.
Right?
Okay, this is a linear scale. Yes, so now it's better. So we are fitting. So this is the stretch exponential, is the red. So if you are this KPZ or XY model or all of these things are long-range behavior. They are not short-range behavior. Short-range behavior is given by microscopics, by the form of the interactions. There are like specific system. So you have to kind of eliminate this short-range behavior, which are usually fitted by the Gaussian. So you can fit first your Gaussian, will fit nicely here. And then from here, more or less, from here, you can go quite a long way. And at that point, you probably want to eliminate because you have periodic boundary conditions. So finally, this will start going up. Yes. So what we do to make sure, we take different system sizes. This is not, of course, I'm just showing you one example. But in numerics, we will take one system size and then increase. So finally, we only fit in the area which doesn't change as I increase the system size. So the last point we eliminate because this affected by the boundary condition and the thing going up. But it's quite, I mean, it's quite a large. And this is also experimentally possible. These are in dimensional units, but more or less it's microns. I think in our dimensional units are more or less 0.87 micron or something like that. So this is more or less microns, and that's the kind of length scales which are usually seen in polariton experiments. Yeah, it's all micron scale.
Thank you. Well, thank you for this very interesting talk. I have actually, my questions are related mostly to the underlying models that you have here. So first I would like to understand what is your understanding about the physical origin of this anisotropy in the Altman's model for this. So the origin of this KPZ emergent physics is because it's intimately related with this anisotropy between X and Y.
No. So KPZ physics is connected. You can have isotropic system and have KPZ. It's connected with nonlinear drive. So you have to have, let's say, if you write your, let's say, Keldysh field theory, or if you write any Hamiltonian, you have to have imaginary term which is nonlinear. So if you think of non-Hermitian Hamiltonians and take nonlinear non-Hermitian Hamiltonians, so I has to be proportional to something which is nonlinear. If you just have like I kappa psi, so the usual decay of the cavity photons, this will not generate KPZ.
Okay.
You have to have I kappa modulus psi square psi.
But my question still remains, what is the origin of these dx, dy that are different? To
These are different.
Yes.
So of course, for KPZ, you don't have to have them different, but just that it helps. This is our work that it helps to have them different because you kind of can make length scale for KPZ smaller than vortices, but you don't have to have them different. You can make them the same and you still have KPZ, but the vortices then will kill you if you want, unless you put some other thing. So our proposal is to put some anisotropy. Jacqueline Bloch proposal is to put this on a lattice. And if you put on a lattice, some of these phase fluctuations are a bit smaller than, the lattice is a different system. Like on the lattice, so I don't know, I have not seen these calculations, but apparently, if you can talk to Anna Minguzzi, because I think she did this calculation, that if you put a KPZ on a lattice, somehow these vortices are also a bit dumped.
Okay.
I mean, not dumped, but just less relevant.
And then a more curious question. So at a certain point you mentioned in these experiments where you have this formation, spontaneous formation of these circles, that it can share some connections with this VICSEC model for active matter. If I understand this properly, VICSEC model, you have these self-propulsion terms, and then you have also this effective orientation. But where is the self-propulsion here in your systems? Where does it come from? What is the active matter part, the active character of these systems?
Well, so this condensate is coupled to reservoir of excitons, and so in our case this is crucial. So if we eliminate this reservoir adiabatically to create just effective equation for the condensate, this physics is lost. So what is important is that you have two time scales in the system, one for reservoir and then one for condensate, and those are coupled. We tried actually with Letizia Cuangiolo, when I was in KTP, we tried to take this equation and derive some kind of effective theory for the phase, but it's not very easy. So, I mean, if someone is able to do, we kind of failed to. So this is numerics. You can see it on the numerical side when you solve this equation. And it's important that you have two time scales in the system. But just to derive equation for one variable for just a phase from these equations is difficult. Like, I mean, so far, of course, like we have many projects, and it's not that I'm spending, a lot of time on it, but we tried when we're in KTP with Letizia, and it's not very easy to do that. But yeah, it's an open question. Maybe one can really derive that and show, it's kind of more numerical result.
Okay, thank you very much. Sorry, I think we should close it here and thank both speakers. And I should say, sorry, we will applaud, but we come back at 35 past just to give enough time for people to have a break. So let's thank both speakers and Marzena. so I guess it's a good time to start or to continue. So that's one talk in each session by Lauriane Chomaz, exotic many-body states in dipolar quantum Bose gases of magnetic atoms.
Okay, thank you. Thank you for the introduction. I would like, is it fine, the microphone? Yeah. So I would like to start by thanking the organizer for having me here. And I'm sorry if I was not always really responsive, but it's really nice to be here and to be participating to this very nice program. So thank you very much. So what I would like to do in this talk, so I'm in Heidelberg actually since 2 years. And what I would like to do in the talk is somehow give you an introduction relatively general on the platform that I've been using in my postdoc, and I'm now also developing in Heidelberg. And this is about ultra-cold magnetic gases of atomic gases. And the first part will be on, let's say, an introduction on this platform, then the discovery of new exotic quantum phases in these systems. That was in Innsbruck, and now the experiment that I want to develop and the idea that I have with this experiment. So to start, and okay, this is also really nicely like reviewed in a really like extensive review that we wrote with many people that are important in this field, and that is now out like in a journal. So to start, I would like to give you an introduction that I hope is like well fitted to this audience about long-range interactions and dipolar interaction in particular. So you know that in the ultra-cold dilute regime that is generally applicable for quantum gases, then the interactions there can be quite simply described. And in particular, if you have interaction that decay as 1 over R to the with a power of n, with n that is larger than 3, then you can approximate this interaction, whatever is the short-range physics, to a contact pseudo-potential, which is written here. And there is only one single scalar parameter that fixes the strength of this contact pseudo-potential, which is the scattering length AS. And this has been, let's say, really powerful for ultra-cold quantum gases because it applied to the dominance force normally between the two atoms, which are the van der Waals interactions, which have n at the power of 6. And therefore, you have this simple description that I apply. And it's even more powerful because you are able to tune this scattering length parameter, but via what we call Feshbach resonance. So that rely on the internal structure of the atoms. So we can tune this parameter really freely from -infinity to +infinity in theory. And therefore we can, like it has been possible in the field, as you can see from the many talks that we have had already in this week, many different systems and regime in these systems. However, there is still a limitation, which is that we cannot go in this system to something that is different from this contact interaction. So it's limited in the variety. And in this sense, is why we introduce dipolar interactions. So as you can see, the dipole-dipole interaction decay with this R power of 3. And therefore, it remains long range even in the ultra-cold dilute regime because you have all partial waves that keep contributing at this low energy. And it's also anisotropic. So that's the general form here for 2 dipole, nu1 and nu2. And you can see that it depends on the orientation of the dipole compared to this interatomic axis. So there are prospects for novel few and many body phenomena. And particular, so there are different platforms where you can find this dipole-dipole interaction. And the particular platform I am interested in is both with a magnetic atom. And in this platform, let's say, the dipole-dipole property varies from the permanent magnetic dipole moment of the atom. So in this periodic table, in the color code of this table, you can see this dipolar length, which sets actually the strength of this dipolar interaction from blue to red, the maximum. And you see with this square that there has been also a trend in the community to cool down atoms that have strong magnetic properties, starting with chromium And more recently with this family at the bottom here, which is that of a lanthanide family. And this is what I will be focused on. So this lanthanide, they have the specificity to have a 4F submerged shell below a closed 6S shell. And this gives them this strong magnetic property, but also many interesting property for cooling and also like a large effective spin. And also what is important is that for dysprosium and erbium, that are the first one to be post-condensed, they have also many different isotopes. So here I give a dipolar length for dysprosium and for erbium. So you see that there is a ratio of roughly 1/2 between the two. Okay, so I have said that in these lanthanide gases, you have these dipole-dipole interactions. And actually what is really remarkable in this system is in fact that you have not only this dipolar interaction, but competition of interactions, in the sense that they are still for the bosonic species or for the bosonic isotope, these van der Waals interactions. And these van der Waals interactions, the dipolar interactions, they're actually of similar strength. So you can still have this contact term that I described to you at the beginning with a background value that is on the order of 100 A0 for this scattering length. And you can see that this is roughly on the same order of the dipolar length. And actually, most of the like remarkable results that came in dipolar Bose gases are related to the competition of these interactions and the tunability of these competitions. And in particular, what we can do is to use Feshbach resonances, as I introduced also to you at the beginning, to tune the value of the scattering length. And by tuning this value of the scattering length, you tune the competition of the dipolar interaction and the contact interaction to reach a regime, for instance, where you have only dipolar interaction or where they are of similar strength or where the dipole dominates or the contact dominates. So that will be like the basis of what I will present to you afterwards. Just to make a small detour, I want to highlight one point, which is the specificity of this Feshbach resonance for lanthanide atoms, and in particular for dysprosium and erbium, which is the fact that, so this is a standard picture of the Feshbach resonance, which rely on the fact that you have different internal states of the atom and different collision channel related to this internal state. And you can have a resonance between one bond state in a closed channel with atoms coming in the entrance channel. And this rely also in interaction between the channel. And what is specific with these lanthanides is because of this large spin, you have many, let's say, number of collision channel. And also you have strong interaction between this channel because of the anisotropic interactions. This anisotropic interaction is not only the dipolar interaction, but also, in fact, the van der Waals interaction, which are anisotropic because of the 4F shell. So you have this really strong coupling, and this leads to many Feshbach resonance. So you have certainly seen already graph like this, where it's low spectroscopy for one isotope. As a function of a magnetic field, we measure like the atom number that are staying into the trap. And you can see these peaks. These correspond to the different Feshbach resonance. So they are a really large density and a dense spectrum of Feshbach resonance that we can use. So there is also interesting physics related to this. I will not discuss it. But what I want to highlight, so I said it's an opportunity because we can tune, but there are also challenges that are important to keep in mind also. So the thing is that there is no possibility to predict really the scattering property of these atoms. And therefore they need to be experimentally characterized. But this is also somewhat difficult because the dipolar interactions, they also play into this characterization. And therefore it's difficult to have a reliable characterization of the scattering length, for instance. So I want to highlight a recent paper that we had, let's say, with a group in Innsbruck on this such characterization that uses really different technique to really know pretty well what is the scattering length in these gases by comparing, let's say, different experimental method in particular. So this was also one check that we had with the erbium experiment in Innsbruck, that we could know really well what is the scattering length. There are also other experimental challenge, which is related to the fact that we use usually also relatively narrow resonance, and there are some losses associated. And the broader resonances, they are difficult to use because they have many feature overlap to them. Okay, so this was a small detour to say it's not completely so trivial, but for now I will go back to this idea of competition of interaction and go back to the fact that I have, let's say, polarized dipole with given dipolar interactions, and that I can tune this contact interaction as I want. And I want to show you now, with presenting you the result that we had in Innsbruck in particular, how this can lead to a new quantum behavior, in particular new phases like the supersolid, by highlighting 2 points: the fact that we can have quantum stabilization and the fact that we can have self-organization. So this goes to my second part. And I will start with the quantum stabilization part. So this is, let's say, the typical picture that you can have from like a mean field description of quantum gases. If you have mean field repulsive interactions, then you have a stable quantum gas. You can form a Bose-Einstein condensate with a finite density. And this has been done in many different species, in particular the lanthanide ones. However, if you have mean field attractive interactions, usually what you would expect is that there is no finite, there is no finite density state. I don't manage to change anymore. No. Ah, okay. Yeah, it's my computer. Wait. Okay, now I could change. Let's see. Yeah, okay. So I wanted to say that there is no finite density state in general if you have mean field attractive interactions. And when you somehow drive the system to this regime, starting from repulsive interaction, what you expect is a fast dynamic marked by implosion and further explosion under three-body effect, which was coined like Bose nova a long time ago. And it could also be observed in magnetic gases in chromium experiment in Tillman 4 group. Oops, sorry. So no, okay. In Tillman 4 group in this paper in 2008, where he saw also a dipolar effect in this Bose nova. However, what was really a big change in the field of magnetic atom was the discovery in 2016 by the same group of Tillman 4 that this does not apply actually for more strongly magnetic atom, and in particular for the case of dysprosium, where they observe that when they try to graph this collapse, what they see is that the gas was staying alive for a quite long time. So the time scale here are hundreds of milliseconds, while here it's below 1 millisecond. And that it forms some sort of density structures within it. So at that time, it was really not understood what was leading to this sort of stabilization. And there were many different theory proposals, and further, let's say later in time, it was understood actually that this mechanism was in fact related to what is called like quantum stabilization law, which is stabilization under the effect of quantum fluctuations. So the idea behind it relates to a work by Dima Petrov in mixture. And it's the idea that you have different interaction of different origins that are competing at the mean field and that have different sign in a way that the total mean field is relatively small, can be positive or negative, but close to zero, while these two interactions in themselves are quite strong. And now, while the mean field interaction is tuned close to zero, what comes into play now is the fact that this condensate is not only a classical field in a sense, but also has a fluctuating part. And there are interactions with this fluctuating part that become dominant. And what is also really nice in our system is that we can treat this fluctuation, like the effect of this fluctuation, into the energy perturbatively. And this is quite reliable because we don't have a strong quantum depletion. And therefore, the term that came into the energy is this Yang parameter, which has been calculated in the dipolar case by our organizer a long time ago also. And this has applied like to many experiments, no? And what is remarkable here is two things. First, that it's a repulsive term. And second, that it's scaled quite strongly or more strongly than the mean field term with the density. Therefore, what happens if you try to drive a collapse is first the density start to increase under the effect of these mean field attractive interactions. But at some point, these terms become dominant and stop this somehow collapse. So that explains the observation, and it has led to many different observations, in particular related to the fact that we can form this droplet state, like single droplet state. And this we also showed in our group in Innsbruck with erbium, and this was the first like isolated droplet and could show also this scaling of this stabilization mechanism at that point. Okay, so this was the point on quantum fluctuation. Now I would like to discuss the second point that I highlighted is important, which is self-organization. And I would like to relate this self-organization to the dispersion spectrum of these quantum gases. And this is really a rough description of what are elementary excitations, but you can see as a wave of density of phase with a given periodicity, which is corresponding to their momentum, and they have a given speed that give their dispersion relation. And this concept of elementary excitation was introduced actually a long time ago by Landau to describe the remarkable property of superfluid helium. And in particular, what he described is that there are two kinds of excitation that are remarkable of low energy. This phonon part here at small momentum, and this minimum at finite momentum, minimum in the energy, which he called the photon. And this was shown afterwards, but it also corresponds to a tendency of a system to crystallize. So now the question is, what are these elementary excitation from our quantum gases? And here again, what is quite nice is that because, let's say, the system is weakly interacting, we can use perturbative theory and use in particular the Bogoliubov treatment to describe this dispersion relation. And here you can see in this description that there are two, let's say you can say you have two kind of contribution to this dispersion relation, the kinetic part and an interaction part, which is momentum dependent. Just from, let's say, basically the Fourier transform of your interaction potential. Now, how does this develop for the quantum gases? In the case where you have pure contact interaction, so your interaction potential is this delta function, the Fourier transform will be just a constant, and then what you would have from this formula is simply something that evolved from photons to quasi-particle without any photons. So one question in the field was how to reintroduce this photon property that you have in superfluid helium into quantum gases. And you can see from this formula, finally, what you want is to reintroduce a momentum dependence. And this you can get if you have long-range interaction and anisotropic interaction. So how is it with dipolar gases? Now, if you have a uniform dipolar gases, what you find actually by doing the Fourier transform of the potential is that you have only angular dependence of the interaction potential in terms of momentum. So you will see that you have anisotropy in the excitation. So you have two different phonons depending on the orientation compared to the dipole orientation. And that's it. You have no new type of excitation, no photons. So this led to the second important ingredient that come into play, which is now the trap. And in particular, if you add a trap which have a strong confinement along the dipole, and you look at the excitation in the remaining direction, what you find is that you can recover this photon And the size, like the typical momentum of this photon, will be given by the inverse of the size of the, let's say, of a trap in this transverse direction. So you can see an intuitive picture of this phenomenon from this typical drawing, which is like, so you look at the excitation along the long direction, and at low momentum, you watch this excitation makes is some sort of density bubbles, but are quite long compared to the transverse direction. So the contribution of the dipolar part is mostly this side by side, so therefore repulsive. So this will like stiffen the dispersion relation. While when you go to larger momentum, at some point you form bubbles that are small compared to the transverse direction. So you have a contribution from the dipolar interaction that are mostly head to tail, no, so attractive, and therefore you will tend to soften the dispersion relation. And because of the competition with the kinetic part, you will find this minimum. So that's the typical picture where you can form a roton in this system. So this was, let's say, in theory, explained a long time ago by different paper by Duncan Odell and Luis Santos in particular in 2003. And it was seen in experiment quite recently. And before showing you the experiment, I want to just highlight another point, which is really particular in our system compared to superfluid helium, which is the ability to really control the softening in the sense. And this comes from the fact that in this interaction contribution, it's not only the dipolar part that comes, but there is still this additional term, which is a constant coming from the scattering length, so from the contact part. And as I said, this contact part, we can tune in strength. So we can really set its value continuously, decrease its value. And when we do this, we can see that it leads to a stronger and stronger roton minimum toward the full softening. So this we showed actually in two sets of experiments in Innsbruck. I will not describe the detail, but just to give you the idea. So there was one set of experiments where we performed Bragg spectroscopy on a stable BC. Actually, we saw already some what is Bragg spectroscopy in earlier talk this week. And mostly we do two-photon Raman excitation, and we measure as a function of the momentum and the energy imparted from this excitation, the response of the gas. And we see, let's say, resonant response, but we trace here and compare also to theory. And we trace this as a function of the scattering length of the gas. And what we saw is the appearance of this minimum in the response. So this was one signature of this roton. And in fact, in an earlier experiment, what we show is signature in the roton rather in non-equilibrium behavior of the system in the dynamics after an interaction quench. And we, when we perform this interaction quench and change the value of the scattering length, what we saw is this remarkable peaks. So this is the density distribution of the gas, and it's in this cigar geometry. So this is the long axis, and this is the short axis, and it's inverted due to the fact that we look at the momentum distribution. And we saw along this long axis that these two side peaks that appear at really specific momentum, and we could show that this corresponds to the roton momentum, and we could show that this like this population here is a coherent population of the roton mode, and it grows also exponentially. So this was the two proof of this possibility to rotonize the system and to control also this rotonization. Now with these two tools at hand, so we have this self-organization with a tunable strength, and we have what I showed you previously, the quantum stabilization. What we can ask is there the possibility to have new, let's say, ground state when we have this full softening, and in particular, can we have supersolid? So as I'm the first in this session about supersolid, I'll give you just a short introduction on what it is. So it will be a state that breaks somehow spontaneously two symmetries. and take two kind of properties, that of solids, so the atoms tend to be localized at certain position of space, and that of superfluid in the sense that they are also fully delocalized. And this idea of having a supersolid, it was discussed like more than 60 years or 70 years ago. First in a paper from Penrose and Ansager, saying that it's not possible to have such a state. And this raised many other theory work that actually proposed the realization for such state going beyond this, let's say, this assumption made by Penrose and Ansager. There were also a really long search for such a state, first starting from solid helium, and there were actually some, let's say, claim that it was observed, but this claim was retracted in 2012. And with the rise of quantum gases, actually, came another direction to look into these questions. Now, starting in a sense from spontaneous of a BEC, of superfluid, and try to induce spontaneous density modulation. So taking some of the opposite direction that what was done in helium, and this linked back to some also really early work by Eugene Gauss in particular. And this has developed since the development of cold atom into a really rich ensemble of theory proposals. And like you can understand from what I tell you before, but what you need is to induce somehow some momentum dependence into the dispersion relation. And there are different platforms when you can do this. And I want to highlight that like there are some first signature of supersolid state that have been observed in different platforms, in particular in spin-orbit coupled BEC and in cavity-mediated interactions, BEC. And here I want to focus on the dipolar case that was related to observation 2019. So in this system, now we can ask first, what can we expect in terms of ground state, taking the ingredient that I told you before. So we can do some like extended mean field calculation where now we take into account the Lee-Wang-Yang term to stabilize the system. And this is the typical phase diagram that you can expect in this geometry. And here taking the value for erbium, actually. And here what we do is varying the scattering length and the atom number in this geometry. And you can see different phases. We have a color and several that you have already seen in this talk. So first this regular BEC where you can have this photon excitation. In blue, what you have is what I showed you actually in the first part, which is this droplet, either single droplet or array of insulating droplets. And now what is remarkable in this phase diagram here is this region more in red. And actually what shows this color code is a decomposition of the state into individual droplets and looking at the overlap of these individual Gaussian droplets. So it will show a certain ability to tunnel between the different droplets. And therefore, this will, in terms of theory, identify what is the supersolid phase. And you can see, so there is such a region. It's rather narrow in terms of scattering length range. That's why also it took some time to realize them. So they are overwork, but also show similar, let's say, phase diagram and theory calculation. This is from our work in Innsbruck. So now the question is how to look at this in experiment. And I want, before to show you the measurement, describe how we could do this, like to probe this system, just using time of flight measurement. I want to distinguish the behavior of these three different phases. No, so if you do a time of flight, this is just releasing the trap and looking at the free expansion of the gas. What do you expect in terms of density in these different cases? So if you start from the homogeneous BEC and you release it, what you will see is just a regular structure. Now, if you look into these two density modulated states, what you expect is to have interference effect between these different, let's say, density structures. But they will behave differently depending on if they have random phases, so if it is an insulating array, or if they are a fixed place relation between the droplets. when you have random phases, what you will see is interference pattern, but always with a random structure. In this sense, when you do the average over many realizations, what you will see is that the pattern disappear in average. Whereas when you have this fixed phase relation, you will always see the same phase pattern, and therefore it will stay in the average. And by using this idea, we created two amplitudes describing the appearance of modulated state via the amplitude of structure in individual images, or of a phase coherent modulated state via the amplitude in a time, like in the average of these images in time of flight. So that's what we did in experiment. We start from a BEC of erbium, and we slowly ramp the scattering length and hold for a certain time. And we look at many realizations of this experiment in time of flight and measure the amplitude A5 and AM. And these are the result of this measurement. And we could see that like there is a regime where you have no amplitude at all. This is the BEC. And when you go below a certain critical scattering length, you can see that there are these two amplitudes going together and staying together for a certain range of scattering length of the order of 1.5 A0. And then it was remaining only for this modulated amplitude, showing that you have first a supersolid and then an insulating array of droplet. So this was this first measurement in erbium. So there were also other related work relatively simultaneously in the group of Giovanni Moduno and Timanfort. And in our experiment, let's say in our experiments in Innsbruck, we could actually not only look at erbium, but also at dysprosium and look at this in a different way, in a sense, but not doing a scattering length ramp, but no, doing really a direct evaporation into the supersolid. And this is related to the property of dysprosium from the fact that it has a larger dipolar length than erbium, so it allows for a longer lifetime. And also for dysprosium 164, that you can tune, like you should tune away from the Feshbach resonance to stabilize the supersolid. So in terms of loss, this is also favorable. So we did this experiment where we start from a thermal gas at a given value of the scattering length and just do evaporative cooling in this configuration. And we could observe in these two different regimes, either corresponding to a supersolid ground state or a BEC ground state, the appearance of this side peak that shows like some of the fact that we have indeed created a modulated state and a supersolid state here, while here we create just a BEC. So at that time, the resolution in this experiment, which was the new experiment, was not really good. That's what the signal is not really good in this case, but we later improved this imaging, and we could even do in situ images of this supersolid, and we could see that it really lived really long, for several seconds, actually. We, in further work, we also studied a bit more in detail this evaporative cooling behavior. And in particular, what we look is inside the realm of its evaporative cooling, while the system, let's say, reach this supersolid state. And is it that from a thermal state, will we create first a superfluid and then a supersolid, or first a solid and then a supersolid? This was the question that we wanted to answer. And what we observed by looking again into this amplitude AM and A5 is that this amplitude AM, which show the modulation, appear first compared to the global phase coherence. So it seems that in general, you form first a solid and then supersolid. So this is not completely a clean system in the sense that we are also changing the trap parameters at the same time as we do this evaporation, and that we are changing the atom number, but it seems that like we try different protocol and it was always what we observed. And in this same experiment, we also look at what happened after, let's say, in holding after the evaporation. And while the super solid diet in a sense. And in this experiment, what we could see, looking now like a different kind of observable, looking at the modulation from in situ images, what we observed was in fact that in this lifetime, so starting from relatively hot samples and cooling down, and then losing atom from three-body recombination, that the system seems to have stronger modulation at higher temperature for the same number of atoms in the quasi-condensate part. So that you can see when you go along this line, but if you have larger temperature here and here, you don't have the same modulation. So it seems that in this system, contrary to what you expect intuitively, maybe for a classical system, you have a solid at higher temperature and the superfluid at lower temperature. And this was actually also like some theory work, relatively recent, that also shows some understanding of this effect. So that's the main part that I wanted to discuss on this super solid. I just want to, in a few slides, highlight what have been the work afterward and what are the open questions still, in a sense. And the main part is related to proving super fluidity in this system. So there have been different works, and the first set of work were related to proving the low-lying elementary excitations in the system. And there were some, especially in our group in Innsbruck, but also in the group of Giovanni Modulo and Tim Alford. And this is what you expect from the elementary excitation in the trap system. And yeah, the main characteristic is that you have these two branches of phonon modes, and these two branches of phonon modes correspond to, let's say, the breaking of these two continuous symmetry. And you can also look at what these modes look like in the time evolution, and they indeed can be identified as crystal modes and phase modes. So there have been experimental evidences related to this. It's not a direct proof of superfluidity, but it relates to at least some dynamical properties that are related to this. There have also been further works, in particular for probing rotation, which will be a quite strong proof of superfluidity, where you can also try to extract the superfluid density, but for now it has not been completely conclusive. And there have been further, let's say, dynamical studies, in particular probing the rephasing dynamics after a quench. The other tendency in this system is to look into more complex structure of the supersolid, and I want to highlight, even if it was after my time, this really nice work in Innsbruck, where they show like towards a two-dimensional structure in this supersolid and also zigzag. Okay, so this concludes the part on the Innsbruck work, and I really want to thank this really great team with whom we did this many experimental like measurements, and in particular, let's say the team leader Francesca Ferlaino, and these two experiments with the erbium was most related to, and also we work really in strong collaboration with erbium dysprosium on the dysprosium supersolid. I thank also all our theory collaborators and our funding. So now in the time that I have left, which I don't know how much it is, I just want to give you a short introduction to what I want to do in Heidelberg, and how this somehow relates strongly to this conference. Because what we want to do is to look now still in magnetic atomic gases, but in lower dimension and also with tailorable properties. So mostly, so this is the lab where I started in 2021, and it's stage at this time. Actually, it was not a optical lab at this time. I just got this table from the neighbor because they could not take it out anyway. And it was a radioactivity lab, so this was like a safe radioactive safe. And now that was what it looked like nearly 1 year after. And now it's like this, but everything is close. And here are all the people that contributed until now in building this experiment. So in terms of the physics that we want to do, as I said, what will be the focus is lower dimension, and in particular 2-dimension. And here, what I want to do also is to have a tailorable trap, like a full control on the trap geometry, and this relates also to some talk that we saw yesterday and this morning on having this 2D setup with a digital micromirror device. And so I want this full control on the trap shape, but I also want full control on the interaction. And for our case, this is a bit specific. So it's not only tuning the scattering length value, but also the orientation of the dipoles compared to the plane. And I will discuss now a few things that we think that we will study. And before this, I want to give you just a small introduction into the physics of vortices in this system, because many of these aspects are related to vortices. And the point that I want to highlight especially is because these vortices correspond into a vortex core, especially, so a density depletion, they can be seen as anti-dipole, so they will have interactions that are of dipolar nature. And this modify, it has been shown in several papers, theory papers, but it modifies their stability as pair and their dynamics. And also it modifies the single vortices property of the system. So what we want to look at. So the first general direction is into equilibrium phases and phase transition in this lower dimensional system. So this doesn't need a lot of introduction because it was really well discussed this morning in particular, and also yesterday. So the idea is that in 2-dimension, you would expect not to have really a conventional ordering, but this type of Berzitsky-Kosterlitz-Fowler's transition that are driven by pairing of topological pairs. So to reproduce this small picture that you have already seen, you have a quasi-ordered phase that occurs for the superfluid case. You have a binding of this vortex-anti-vortex pair, and you have a proliferation above the certain critical temperature of free vortices, and this will be the disordered phase. And this transition occurs, you have a competition, let's say, between energy, in fact, energy and entropy, and this comes from the fact that they both scale as the logarithm as the system size, mostly. And now the question is, if you have long-range interaction, and in particular dipolar interaction, well, this will be modified in a sense. Like, is the dipolar interaction breaking this logarithm scaling, or is there some screening effect? And so there have been a lot of like at least some theoretical work on this, and there were some debate. I think for certain case, now it's quite clear that there will be a BKT transition, just some shift. Yet it's not fully studied, I think, in our specific system, where you have also anisotropy and where you have interaction competitions between dipolar interaction and contact interaction, plus also over term in a sense. So that's one part of the question. And now, of course, I introduced to you, like in this first part, a lot about this new order. And this is also a question in this direction. If you have supersolid or droplet crystal, like you have new, like you are breaking a different kind of symmetry, and you can also have a sort of BKT transition related to this new order. And this involves new kind of topological defects that are not the vortices, but are dislocation or disclinations of this crystal. And is the question, wow, let's say, wow, these two physics interplay, in particular in the supersolid, what you will have. And can you have also intermediate phases, like in comparison to liquid crystal, for instance? Okay, so this will be one direction that we will be really interested to look at in experiment. And the other direction, also really related to what we learned this week, is related to dynamics. And one part is far from equilibrium dynamics. And this also need no introductions, but if you look into this, as we have learned this week, it's really related to wave excitation and to vortices and the way the system evolves, let's say the cascade or any universal scaling or rethermalization occur microscopically via some vortex dynamics, in particular recombination or annihilation, and the interplay of this with different waves, let's say. And now the question that we can ask in this system where we have dipolar interaction is what will be, let's say, the new behavior that we can expect from the fact that we have no dipolar interaction between the vortices, that we have anisotropy. And also what happens if we have a roton, so we have a non-monotonic dispersion for these two interplay, and what is the role, let's say, of the interaction competition, again, with the underlying phases that we can change. And there were some some theory work a few years ago that give a first look into this system of quantum ferrofluid turbulence. And they tend to see that you can have different scaling when the dipolar interaction tends to dominate. So this was still in 3D. And I think there are still a lot to explore in this direction, also in theory, actually. And okay, and the last point that we would like to study is also, again, related to some talk yesterday, what are the dynamics at the phase transition? Know that you have all these different phases, and there are actually many open questions on what is the order of the phases, what are the universality class here. So I think, yeah, it's a really open system. Okay, so this is what we want to study, just to give you a small introduction to the setup. So this is roughly how it looks like not exactly actually, it's more complex, but yeah, 6 months ago. And you can see the main characteristic, I hope. So here is the oven, and here we have the first cooling stage. And here is the main chamber where we do the experiment. And here, at this point, we have a light for the 3D mode. Okay. And I will give you a few details on what we want to do around this main chamber for the physics that we want to do. So as I said, like we want to have this tailorable geometry and also a really good resolution imaging without going to single atom level, but good resolution. And for this, it's based on 3 main ingredients. First, a microscope objective that we can set like in these 3 entrant viewports. Then an accordion lattice setup that allows to do this 2D confinement with tunable geometry, similar to actually the group of Jean Dalibard that we saw yesterday. And we want to have, let's say this, INA will give some micron resolution and can be used also with special light modulator, in particular digital micromirror device to make a tailorable confinement and also dynamical in the plane. The second point is, as I said, the control of the interactions. And in particular, what we want to tune is the magnetic field amplitude to tune the scattering length, but also the magnetic field direction. And for this, we design like 3 pair of coils that are really close to the experiment to be able to do this fast, to this tuning quite precisely and relatively fast also. The other specificity of our setup, maybe it's only interesting maybe for experimentalists, but is that we have developed a new cooling scheme to reach, let's say, ultra cold gases of dysprosium. And this is based on a 2D or a 2-dimensional magneto-optical trap, which is in this part here. And this directly loads now aligned 3D modes. So there are benefits of this kind of system. In particular, there is no direct view of the oven compared to the science chamber. And there are more free optical access in this case, at least for the typical dysprosium setup. And yeah, we have quite compact setup compared to what you usually have. There were some challenges, and therefore we were not sure what to expect, but we were really happy that we could achieve really good numbers, and I will show you quickly what we have seen. Okay, we got our first 2D mod in April last year, and from this we could load the 3D mod in May. And after some optimization, we could see that our atom number on temperature that we could reach are also really good compared to what is done in the literature with other Zeeman-based setup. And this has given a new publication that is appeared, I think, last week or something like this on arXiv. And yeah, you can have a look if you are interested. And right now, we have also loaded the optical dipole trap, and we have a good loading, and we are currently optimizing the evaporative cooling. And we hope to have to go to the next step soon. And yeah, to conclude, I want to thank the people that are now working on the experiment. So we have already had quite some change of generation on this team. And yeah, thank you for your attention.
Thank you very much for a great talk and exactly perfect time in 50 minutes. Impressive.
Yeah, nice experiments.
Thank you.
So I wanted to ask about this Roton minimum.
Yeah.
Is it always associated with supersolid? Does a supersolid need a Roton minimum in the dispersion?
I think so. On one side, you can have a Roton and not have a supersolid, I think. It means a tendency to crystallize, but the supersolid is more than a tendency to crystallize. You need to crystallize and keep superfluidity. So in like opposite to your question, like you could have a Roton and not have a supersolid. In the other direction, I think you need some momentum dependence of dispersion.
Well, there's the example of liquid helium, in which we know there is a Roton minimum.
Yeah.
But at the same time, it looks like it's not a supersolid.
Yes. So because like if you form, like if the transition from the superfluid to the solid is too discontinuous, you cannot keep the superfluid in a sense. You will form a solid.
Hi, Lauriane. Thank you for the talk.
Thank you.
I wanted, well, it's one doubt I have when finding your presentation. You said that probably DKT transition will happen on your new system, but the critical temperature will be maybe shifted.
Yeah.
And so since the system is no longer scale invariant, once you have the dipolar interactions, do you expect to have the same universal jump in the superfluid density, independent of the interactions? Or, well, I don't know if people already predicted some correction to this jump. Yeah.
Yeah, I don't know. I'm not the expert, but maybe yes, you want to comment.
Thank you. We have yesterday, today in the afternoon, I will show our results on the PKT in 2D, and it's a universal jump as expected. Of course, the anisotropy changes the critical temperature as a function of the anisotropy, but the scenario, as it cannot be in other way, in 2D is PKT. There's no other option, to my understanding.
But let's say there were early debate because you have, let's say, you can reestablish PKT because you have screening effect or in a sense of vortex interactions. And yeah, there were early debate if this is really applying for dipole-dipole interactions in a sense. And if you don't have n to the 3 and equal 3, but n equal 4, then this does not apply in particular. Or let's say there are some theory work on this. I am not a specialist of this. But, yeah.
So I think it's a great experimental progress to measure now also the temperature. I think the first one was in 2021. But what was the experimental difficulty? Because I remember that for many years, one didn't have any access to the temperature.
So temperature of supersolids, you know.
Yes, or droplet.
So droplet is quite difficult because, depends, because if you have no trap, then it's really like there is no thermal fraction remaining. So this was the difficulty with droplet. If you have a droplet in a trap or a supersolid, it should be in a trap, then you have a thermal fraction and you can try to analyze the wings. And this is what we did in this experiment, to just analyze like far away from what is like modified by the quantum state, to just look at the thermal fraction.
Thanks for the clarification.
Can I also follow up? So in these individual droplets, where you have them all individual, are they really completely periodic, or is there any residual fluctuation maybe associated with some residual thermocloud that could make them not completely?
You mean in the in situ distribution? I think, yeah, it's difficult to be conclusive on this.
So there's no underlying reason why they should be exactly periodic. There could be fluctuations that change.
Yes,
sort of
there were some studies from the group of Tillman 4 on what is really the fluctuation, like trying to extract the fluctuations of these different states, and they see like that when you get to this insulated droplet regime, you have different peaks actually that remains. And so there seems to be fluctuation. It's not really clear where it comes from. Let's say.
Okay,
but I was fixing this thing.
Any more questions?
Yeah.
Congratulations for, wonderful experiments, and I see that your progress in Heidelberg is very fast.
Thank you.
My question is a very simple one. When you have this dipolar gas, the interaction vortices, it's modified.
Yeah.
And then going, like going from disorder to order, like by clustering the vortices and anti-vortices, may have something in between, right? Hard time to understand how I'm going to produce that without really modifying a lot the polarization of the sample. So
now you mean for BKT?
Yeah, I think there is something in between that's missing in this scenario. Going for a disorder of vortices, which I already think is hard because there will be many conditions on the dipole and everything. And then I go to the clustering, like Onsager type of formation, and something in between with the dipole must happen. Do you have an idea, or am I thinking wrong?
Let's say for the superfluid, I would not think that there is really something in between. For the supersolid order, I would understand that there can be something.
No, I'm talking about your plans on the,
Yeah.
You said that you're gonna do the 2D,
Yeah.
and you're gonna put the vortices, and that will go.
Just from the vortices.
Yeah. It may be many steps in between going from this inverted cascade.
It can be.
If you want to comment on that.
It's just a very quick question about the inclusion of the quantum fluctuations. By the way, congratulations on your progress.
Thank you.
I'm really looking forward to your success. There's a difference when you start with, for example, 3D system, you calculate the fluctuations and you do dimensionality reduction. But you could also calculate the excitation. So you go, for example, with the Rotom spectrum, and then you do the calculation of the Lewongian correction.
Yes.
So what is the orders that you should do this?
For now, it has been done only via local density approximation. All this treatment of experiment we have done only via local density approximation. So you take the like homogeneous gas result of
Your calculation is 3D, right?
Yes,
So
3D uniform.
And then you do the reduction. But the fluctuations that you get near the Rotom minimum.
Yes.
So when you are softening the mode, you have fluctuations that are more expressive than the fluctuations that you get in 3D. So if you do the calculation of the depletion in that conditions.
Yeah. No, it's for sure one of the open question of stabilizing supersolid, for instance, really in 2D, but you can have different scaling of Lewongian. maybe it can be helpful, maybe it can be like detrimental. This is not completely clear, but I think still that this treatment, it is so, let's say, successful, even if it's like quite wrong in a sense, because the modes that contribute to it, they are the ones that are not so affected by the trap. Let's say, that's my view. But yeah,
Lauriane, thank you for the presentation. It was very nice.
Thank you.
I was wondering about your phase measurements in the droplets. So you say when they are basically decoupled, you have individual droplets, they have no phase coherence, so you don't see any interference pattern, but then you see the phase pattern kind of coherent when it's a super solid. This phase or the of where the droplets appear, is it random? So I mean, I would expect that there's some symmetry breaking, right? So
let's say
you always have in each realization you have a different phase for your droplets.
yes, the global phase, you mean?
Of the, sorry, of the where they sit.
Yes,
Okay.
I see. So this should be random if you have a really a flat trap.
Okay.
It's not the case in experiment, really. Like you see either symmetric or anti-symmetric compared to the trap.
Density is somehow pins.
Yeah, but still, like if you think about what I showed for the time of flight measurement, this is not affected by a global phase. Huh? Like it's only the relative phase between the droplet that counts.
Yes.
Yeah.
Okay, there doesn't seem to be another burning question, so let's thank Lauriane again.
Thank you.
And I guess we're back here at 2 o'clock, right?